Look up at the night sky on a clear evening. You see the familiar pinpricks of light, the steady glow of planets, the silent arc of the moon. It all seems so orderly, so permanent, so understood. But what if I told you that this peaceful cosmic scene is a grand illusion? Our solar system, the very place we call our celestial home, is teeming with secrets that defy explanation, with phenomena so strange they challenge the very foundations of what we think we know. What if the quiet neighborhood we've mapped and studied is actually a stage for mysteries we are only just beginning to perceive? We gaze at the stars and feel a sense of wonder, but just beyond the reach of our everyday understanding lies a reality far more bizarre and captivating than we ever imagined. This isn't just about distant galaxies or black holes light years away. The greatest puzzles are hiding in plain sight, right here in our own cosmic backyard. From the haunting, silent face of our own moon to the frozen, uncharted realms at the very edge of our sun's influence, our solar system is a treasure chest of the unexplained. We have sent probes to every planet, mapped countless asteroids, and yet with every answer we uncover, a dozen new, more baffling questions emerge. These aren't mere curiosities. They are profound scientific enigmas that push the limits of human knowledge, suggesting that our understanding of physics, of history, and of our own place in the cosmos is still wonderfully, thrillingly incomplete. Today, we begin a journey to explore 25 of these incredible phenomena. We will venture from the cryptic, swirling storms of Jupiter to the impossible, tumbling motion of distant interstellar visitors. We will confront anomalies on Mars that look eerily artificial and delve into the strange, rhythmic radio signals from Saturn. Each mystery is a piece of a grander puzzle, a clue that hints at processes and possibilities we have yet to dream of. This is more than a list. It is a voyage into the heart of cosmic curiosity, a testament to the fact that the universe is far stranger, far more mysterious, and infinitely more interesting than we have been taught. So, let's set aside our textbooks and prepared answers for a moment, and embrace the beautiful, humbling, and exhilarating unknown. Our journey into the unknown begins not in the far reaches of the outer solar system, but with our closest and most familiar celestial companion, the Moon. For centuries, it has been a symbol of constancy, its silent, cratered face a testament to a world frozen in time. We've walked upon its surface, driven rovers across its plains, and yet it holds a profound secret that challenges our most basic assumptions about how rocky worlds evolve. The mystery lies in something we can't even see with our eyes, a magnetic field. Today, our moon is a magnetically quiet place, lacking a global magnetic field like the one that protects Earth from the sun's harsh radiation. But when Apollo astronauts brought back samples of ancient lunar rock, scientists made an astonishing discovery. Locked within those rocks was a record of a powerful magnetic field, one that likely existed billions of years ago. It's as if we found a fossil of a mighty heart still beating within a long-dead body. This creates a fascinating puzzle because the leading theory for how planets generate magnetic fields, known as the dynamo theory, runs into a major problem when applied to the Moon. A planetary dynamo requires a molten, churning metallic core, acting like a giant electrical generator. But the Moon is small. Its core should have cooled down and solidified relatively quickly after its formation. According to our models, a lunar dynamo powerful enough to create the magnetism found in those rocks simply shouldn't have lasted for the hundreds of millions, or even billions, of years that the evidence suggests it did. So, what could have powered this ancient lunar force field? One compelling idea points to cosmic violence. Imagine a period in the early solar system, a time of chaotic bombardment. A truly massive asteroid impact striking the Moon with unimaginable force could have shaken its entire interior. This colossal impact might have stirred the Moon's molten core back to life, like a giant spinning a drink in a glass, temporarily reigniting the dynamo for a short, intense period. Another hypothesis suggests the Moon's early orbit may have created unique gravitational forces, a complex tug of war with the Earth that kept its interior hot and mobile for much longer than we thought possible. Unraveling this mystery is far more than an academic exercise. It forces us to reconsider the very life cycle of planets. If a small world like the Moon can sustain a long-lived magnetic field, what does that say about the potential for life on small, rocky exoplanets orbiting distant stars? A magnetic shield is often considered a key ingredient for a habitable world, protecting a nascent atmosphere from being stripped away by stellar winds. The Moon's hidden magnetic past suggests that the conditions for such protection might be more common or more complex than we ever dreamed. It reminds us that the quiet, seemingly inert worlds we see today may have once been dynamic, energetic places with their own dramatic and hidden histories. From the silent, magnetic mystery of our Moon, we turn our attention to the very star that gives us life, and a paradox that cuts to the heart of our own planet's history. Our Sun, that brilliant, steady source of light and warmth, has not always been the same. Astrophysical models tell us with great certainty that billions of years ago, when life was first taking hold on Earth, our Sun was considerably fainter, about 30% dimmer than it is today. Think about that for a moment. If you were to reduce the Sun's output by nearly a third right now, our world would rapidly transform into a global, frozen ice ball, a snowball Earth with oceans locked solid under miles of ice. And yet, when we look at the most ancient geological records, the evidence is unmistakable. We find rocks that could only have formed in the presence of liquid water, and fossilized traces of microbial life that date back to this very same era. So, here is the faint young sun paradox in its full, baffling glory. The climate was warm enough for water to flow and for life to begin, under a sun that, by all rights, should have made such a thing impossible. How did our planet solve this cosmic heating problem? The most widely accepted solution points to Earth's early atmosphere acting like a super-powered thermal blanket. Today, we worry about greenhouse gases like carbon dioxide trapping too much heat, but back then, a much thicker atmosphere, potentially rich with powerful greenhouse gases like methane or even ammonia, could have provided the necessary insulation to keep the planet cozy. This ancient air might have created a profound greenhouse effect, compensating for the weak sunlight and creating the stable, temperate conditions that life required to emerge. But this seemingly elegant answer comes with its own set of complications. For instance, a methane-heavy atmosphere would have had a limited lifespan as it's broken down by sunlight. To maintain the warmth for the hundreds of millions of years indicated by the geological evidence, there would have needed to be a massive, continuous source of methane, perhaps from a world dominated by methane-producing microbes. This introduces a fascinating chicken and egg scenario. Did the conditions for life create the atmosphere, or did the atmosphere create the conditions for life? Other theories suggest that the young Earth's surface was much darker, perhaps covered in vast expanses of black volcanic rock that absorbed more solar energy, or that its cloud cover was profoundly different, trapping heat more effectively than today's clouds. There's even the provocative idea that Earth's orbital characteristics were different, bringing it closer to the Sun for periods of time, though this lacks strong supporting evidence. Each proposed solution is a piece of a puzzle, but none perfectly snap into place without creating new questions. The real power of this paradox is what it reveals about the delicate, dynamic balance that makes a world habitable. It suggests that planets have thermostats, complex, interlocking systems of geology, atmosphere, and even biology that can work in concert to maintain stability against cosmic odds. This isn't just a question about our past, it's a guiding principle in our search for life beyond Earth. When we look at distant exoplanets orbiting other stars, the faint young sun paradox teaches us that a star's brightness alone doesn't tell the whole story. A world that might seem too cold at first glance could, through its own atmospheric or geological magic, be a perfectly warm cradle for life. It's a humbling reminder that our planet's history is a narrative of improbable survival, a story of how a fragile sphere of rock and water found a way to stay warm against the cosmic cold. Now, let's travel from the paradox of our warm young Earth to a world that represents its ultimate, terrifying opposite, the planet Venus. Often called Earth's sister planet, Venus is nearly identical to our own world in size, mass, and composition. It formed in the same neighborhood from the same fundamental materials, and yet to call Venus our sister is a cosmic misnomer. It is more like our evil twin. The surface of Venus is a true vision of hell, with a crushing atmospheric pressure 92 times greater than Earth's and an average temperature of 860 degrees Fahrenheit, hot enough to melt lead. The sky is a perpetual, suffocating blanket of yellow clouds that rain sulfuric acid. How could two planets born so similar end up on such extraordinarily different paths? The answer lies in a process known as the runaway greenhouse effect, and while we understand the mechanics of this disaster, its precise origins remain one of the solar system's most sobering puzzles. A greenhouse effect in itself is not a bad thing. In fact, it's essential for life on Earth. Our atmosphere naturally traps a small amount of the sun's heat, keeping our planet at a comfortable average temperature. But on Venus, this process spiraled catastrophically out of control. Imagine a simple feedback loop with no off switch. It likely began with liquid water on the surface. If Venus ever had oceans, the increasing heat from the sun would have caused more water to evaporate. Water vapor is itself a potent greenhouse gas, so more vapor in the atmosphere would trap more heat, which would in turn cause even more evaporation. This self-reinforcing cycle would have continued until the planet's oceans literally boiled away, filling the atmosphere with a massive, heat-trapping blanket of vapor. High in the atmosphere, solar radiation would have then split the water molecules apart, with the lightweight hydrogen escaping into space forever and the oxygen combining with other elements. This was the point of no return, the irreversible loss of Venus's water. With no oceans left to absorb carbon dioxide, the vast amounts of CO2 released from volcanoes and surface rocks would have built up in the atmosphere with nothing to scrub it out, creating the immense, crushing, and superheated CO2-dominated atmosphere we see today. So we know how it happened, but the profound mystery is why it happened to Venus and not to Earth. What was the specific trigger that sent our sister world over the edge? One leading theory points directly to the Sun. As our star has gradually grown brighter over billions of years, it eventually reached a critical threshold for Venus. Being closer to the Sun than Earth, Venus receives nearly twice as much solar radiation. There may have been a point where the intensity of sunlight became just enough to initiate that initial, unstoppable evaporation process that Earth, farther out, managed to avoid. Another compelling idea involves volcanoes. Perhaps Venus experienced a period of absolutely planet-wide apocalyptic volcanism, flooding the atmosphere with colossal amounts of CO2 in a relatively short geological time. This would have supercharged the greenhouse effect rapidly, boiling the oceans before any geological or chemical process could intervene to sequester the carbon. The planet's incredibly slow rotation may also have been a key player. A day on Venus is longer than its year. It takes 243 Earth days to complete a single rotation. This sluggish spin could not generate a protective magnetic field, leaving its atmosphere fully exposed to the solar wind. More critically, the slow rotation creates a unique atmospheric circulation. Without a rapid spin to distribute heat evenly, the planet may have developed extremes of temperature that destabilize the climate. or it might have prevented the formation of a protective cloud layer that could have reflected sunlight back into space, a natural sunscreen that Earth benefits from. The true enigma is the sequence. Did a volcanic apocalypse kickstart the runaway effect, or was it the slow, relentless brightening of the sun? Did the lack of a magnetic field allow the solar wind to strip away a protective layer of atmosphere first, making the planet more vulnerable? We simply do not know the exact chain of events. The haunting lesson of Venus is that a stable, habitable climate may be a far more fragile and precarious state than we appreciate. It stands as a permanent warning, a demonstration of how a planet so similar to our own can transform into a sterile furnace, raising the unsettling question of whether such a fate could ever, under different circumstances, await our own world. Leaving the scorching greenhouse of Venus behind, we arrive at a world that has long captivated our imagination as a potential abode for life: Mars. The red planet presents us with a detective story written in the very air itself, a mystery centered on a simple gas with profound implications: methane. On Earth, methane is a common molecule. It's the main component of natural gas. It bubbles up from wetlands, and it's a byproduct of the digestive systems of cattle and other animals. Critically, the vast majority of methane in Earth's atmosphere is produced by living organisms, past and present. This is what makes its detection on Mars so electrifying. If life ever existed, or perhaps even still exists in some hidden niche on Mars, it might just be leaving a chemical signature for us to find. But the plot thickens considerably because methane can also be created through entirely non-biological, geological processes. The Martian methane mystery isn't just about its presence, it's about its bizarre, almost ghostly behavior that defies easy explanation. Our instruments, both on orbiters circling the planet and rovers trundling across its surface, have confirmed the presence of this gas. The Curiosity rover, for instance, has repeatedly sniffed out methane in the air inside Gale crater, but the data reveals something far stranger than a constant background level. The methane appears in sudden, unpredictable spikes. It will be absent for weeks or months, and then concentrations will suddenly soar to many times their usual level, only to vanish again just as quickly. Furthermore, observations from space have sometimes shown localized plumes of methane rising from specific regions of the planet. This transient and patchy nature is the core of the puzzle. If the methane were being produced by some slow, steady geological process, we would expect it to be distributed more or less evenly across the atmosphere and to persist for centuries, as methane molecules are quite long-lived. The fact that it appears and disappears so rapidly suggests that something is actively producing it and that something else is actively destroying it, creating a dynamic and hidden cycle right beneath our feet, or rather, our rover's wheels. So, what could be creating and then removing this gas with such speed? Let's first consider the non-biological suspects. A process called serpentinization is a prime candidate. This occurs when certain types of iron and magnesium-rich rocks, like olivine, come into contact with water. A chemical reaction takes place, producing minerals called serpentines and, as a byproduct, methane. We know Mars has water ice and likely had vast amounts of liquid water in its past. It also has the right kind of rocks, so it is entirely plausible that deep underground, where liquid water might still persist, this geological process is slowly creating methane that then seeps up through cracks and fissures in the planet's crust. Another possibility involves the breakdown of ancient organic material delivered by meteorites. Over billions of years, carbon-rich dust from asteroids and comets has settled on Mars. Ultraviolet radiation from the sun could be slowly processing this material, releasing small amounts of methane. But then we come back to the baffling spikes and plumes. While serpentinization can produce methane, it's generally thought of as a slow, steady process. Could it really explain sudden, localized bursts? Some scientists propose that the methane could be stored underground in icy cage-like structures called clathrates. These clathrates could act like pressurized natural gas tanks, holding the methane until a small geological shift, a change in temperature, or even a tiny Mars squawk causes a seal to rupture, releasing a concentrated puff of gas into the atmosphere. As for its rapid disappearance, the thin Martian atmosphere offers little protection from the sun's harsh ultraviolet radiation, which is known to break apart methane molecules relatively quickly. There's also the possibility that the methane is reacting with the salty, peroxidized soil, effectively getting scrubbed from the air as it touches the ground. Of course, the most thrilling possibility remains biology. Imagine a scenario where simple microbial life forms, perhaps resembling the methanogenic archaea found deep in Earth's rocks and oceans, are eking out an existence in hidden aquifers or porous rock deep below the frozen Martian surface. Shielded from radiation and cold, these organisms could be metabolizing hydrogen or carbon dioxide and producing methane as a waste product. A sudden release of this gas from their subsurface habitat could explain the transient spikes that Curiosity detects. The localized nature of the plumes could point to specific, isolated oases where these conditions are just right. This is precisely why NASA's Perseverance rover is now on the case, equipped with even more sophisticated instruments to analyze the Martian air. Its mission isn't just to detect methane, but to study its carbon isotope ratios. Here's why that's a potential game changer. Life on Earth prefers to use the lighter carbon-12 isotope over the heavier carbon-13. As a result, biological methane on Earth has a distinct light carbon fingerprint. If Perseverance can analyze the methane on Mars and find that it, too, is enriched in carbon-12, it would be the strongest evidence yet that we are not alone, that Mars harbors its own native life. A heavier signature would point more strongly toward a geological origin. The Martian methane mystery is a perfect example of how a single, simple molecule can hold two utterly different futures for our understanding of the universe, one where Mars is a geologically interesting but dead world, and another where it is a second outpost of life in our solar system. Every unpredictable whiff of gas brings us closer to an answer that will redefine our place in the cosmos. Just when you thought you'd encountered every kind of planetary oddity, our solar system presents us with a world so fundamentally skewed it seems to defy the very concept of up and down. Journey with me now to the icy outer reaches, to the seventh planet from the Sun, Uranus. While every planet in our system has some degree of axial tilt, the angle between its rotational axis and its orbital plane, Uranus is in a league of its own. Earth, for comparison, is tilted at a comfortable 23.5 degrees, giving us our familiar seasons. Uranus, however, is tilted a staggering 98 degrees. This isn't just a slight list, this is a planet that essentially orbits the Sun on its side, rolling around its path like a giant celestial bowling ball. This extraordinary orientation has consequences that are as dramatic as they are bizarre. Imagine seasons that stretch for decades. As Uranus makes its 84-year-long journey around the Sun, each pole is pointed directly at our star for 21 years at a time. This means that for a quarter of its year, one hemisphere experiences continuous daylight, a single, unending summer day that lasts for 42 Earth years. Meanwhile, the other half of the planet is plunged into a profound, deep space winter of total darkness that also lasts for 42 years. The concept of a midnight sun or a polar night is taken to an almost unimaginable extreme. Only during the brief transitions between these epic seasons does the sun rise and set in a way that would seem remotely familiar to us, and even then, it would race around the sky in a peculiar circular path. Such a profound anomaly demands an equally profound explanation, and the one that scientists favor is as violent as it is simple: a colossal impact. The prevailing theory suggests that in the chaotic early days of our solar system, a young Uranus was struck a glancing blow by a protoplanet, a developing world roughly the size of Earth. This wasn't a gentle nudge, it was a cataclysmic event of almost incomprehensible force, a sideswipe so powerful that it literally knocked the entire planet over onto its side. The impactor itself would likely have been shattered, its material either absorbed into Uranus or scattered into space. This single, defining moment of cosmic violence could have reoriented the planet's spin axis in one fell swoop, setting it on its unique rolling path for the rest of its existence. It's a clean, elegant explanation that fits with our understanding of how chaotic planetary formation can be, but as with any good mystery, the plot quickly thickens. The collision theory is compelling, yet it raises a host of new and puzzling questions. The most significant of these involves Uranus's entourage. This ice giant isn't alone. It's accompanied by a family of at least 27 known moons and a system of faint, dark rings. And here's the truly baffling part. These moons and rings are also tilted, orbiting perfectly around Uranus's equator in the same 98-degree plane as the planet's rotation. At first glance, this seems to make perfect sense. If the planet was knocked over, everything that formed from the resulting debris disk would naturally inherit that same extreme tilt. But that's precisely where the problem lies. A collision violent enough to tip over an entire planet would have been unimaginably energetic, releasing so much heat that any pre-existing moons would have been vaporized, and any disk of debris from the impact would have been intensely hot. According to our models, the moons we see today, composed largely of ice and rock, could not have condensed from such a seething, post-impact inferno. The heat would have prevented the ices from solidifying. This suggests that the moons must have formed much later, after the planet and its new orientation had already cooled down. So if the moons came later, how did they end up aligning so perfectly with the planet's dramatic tilt? How does an entire satellite system decide to fall into line with a knocked-over planet? This inconsistency has forced astronomers to consider alternative, or at least supplementary, theories. Perhaps the tilt wasn't the result of a single, giant impact, but a series of smaller, successive collisions that gradually pushed the planet over, a process that might have been less disruptive to any potential moon-forming material. Another, more complex idea involves gravitational resonances. In the early solar system, the orbits of the giant planets are thought to have migrated. It's possible that Uranus became caught in a powerful gravitational tug-of-war with Jupiter and Saturn, a resonant interaction that over millions of years slowly torqued the planet onto its side. This slower, more graceful process could have allowed any forming moons to gradually adjust their orbits alongside the planet, maintaining their equatorial paths without being destroyed. Yet, even this theory has its own challenges in perfectly matching the Uranian system we observe today. The shared tilt of Uranus and its rings and moons remains a coordinated event that we don't fully understand. It presents a cosmic crime scene where the evidence points clearly to a dramatic upheaval, but the precise sequence of events, the how and when, continues to elude us. This single, tilted world forces us to refine our models of planetary formation and evolution, reminding us that even the most elegant theories must eventually confront the messy, complicated, and wonderfully strange reality of the cosmos. From the serene, tilted majesty of Uranus, we plunge headlong into a tempest of a completely different order, a swirling vortex of unimaginable fury that dwarfs any storm our planet has ever seen. Behold Jupiter's great red spot, the solar system's most famous and enduring atmospheric enigma. This is not merely a storm, it is a colossal anticyclone, a high-pressure behemoth so vast that our entire planet Earth could fit comfortably inside its swirling crimson boundaries. What we are witnessing is a hurricane that has been raging for at least 190 years, with historical observations suggesting it might even be centuries older. In a universe of constant change, the Great Red Spot stands as a monument to persistence, a whirling engine of wind and cloud that defies our understanding of how weather systems live and die. The central mystery of this Jovian giant is not just its size, but its staggering longevity. On Earth, even the most powerful hurricanes draw their energy from the warmth of the ocean, and once they move over land or cooler waters, they quickly sputter out within days or weeks. The Great Red Spot has no such ocean beneath it, only endless layers of turbulent gas. So, what is the secret to its centuries-long lifespan? The answer appears to lie in a marriage between Jupiter's internal furnace and the planet's complex atmospheric ballet. Unlike Earth, which is heated primarily by the Sun, Jupiter radiates more than twice the heat it receives from our star. This immense internal heat, left over from the planet's formation and sustained by the slow gravitational compression of its massive body, wells up from the deep interior. This creates a vertical conveyor belt of energy, with hot gas rising and cooler gas sinking, driving the planet's violent weather from below. The Great Red Spot acts like a masterful atmospheric machine, tapping into this constant upwelling of energy to sustain its furious rotation. But an energy source alone isn't enough to explain its remarkable stability. The storm's survival is also a delicate dance with its surroundings. Jupiter is famously banded, with alternating east-west jet streams of unimaginable speed creating the planet's striped appearance. The Great Red Spot is nestled perfectly between two of these powerful jet streams, one flowing to the east and another to the west. These raging rivers of wind effectively shepherd the storm, preventing it from drifting into disruptive regions and helping to recycle its energy. The storm itself is a tightly wound anticyclone, meaning it rotates in the opposite direction to the low-pressure systems we're familiar with on Earth. This high-pressure, clockwise spin seen from above creates a stable, coherent structure that is remarkably resistant to being torn apart. It consumes smaller storms that wander too close, growing fat on their energy and momentum, in a perpetual demonstration of celestial survival of the fittest. Yet for all its enduring power, the Great Red Spot is not immutable. Careful observations over the past century have confirmed that it is shrinking. Once large enough to swallow 3 Earths, it is now only slightly wider than our own planet. This gradual diminishment adds another layer to the mystery. Why is it shrinking, and will it eventually vanish? Some scientists suggest that the storm may be encountering changes in the jet streams that confine it, or that small, turbulent eddies around its edges are slowly eroding its structure, sapping its energy like a steady drip of water wearing away a stone. Despite this slow decline, the storm's core wind speeds have not diminished. If anything, they may have even increased as the storm contracts, much like a spinning ice skater pulls their arms in to spin faster. This resilience in the face of shrinking confounds our computer models, which consistently predict that such a storm should have dissipated long ago under the intense turbulent forces of Jupiter's atmosphere. The models struggle to replicate the complex, three-dimensional nature of the spot, which is not a flat feature but a structure that may extend dozens or even hundreds of kilometers deep into the planet's interior, rooting it firmly in the churning depths below. The final piece of this puzzle is its iconic color. What gives the Great Red Spot its distinctive brick red hue? The prevailing theory points to chemistry high in the Jovian atmosphere. As the storm's powerful winds carry gases upward from warmer layers below, these compounds are exposed to the sun's intense ultraviolet radiation. It is thought that this sunlight acts upon chemicals like ammonia and acetylene, perhaps interacting with sulfur or complex phosphorus compounds in a photochemical reaction that creates a reddish chromophore, a color-bearing molecule. The exact recipe remains unknown, but the color itself seems to be a badge of the storm's power, a testament to its ability to dredge up material from the hidden depths and expose it to the light of space. The Great Red Spot, therefore, is far more than a beautiful curiosity. It is a dynamic, evolving laboratory that challenges our grasp of fluid dynamics and planetary climatology. Its continued existence, even in a diminished state, offers a humbling lesson. The forces that shape the giant planets operate on a scale and over timelines that we are only beginning to comprehend, reminding us that some of the universe's most powerful engines are also its most patient. But if you thought Jupiter's great red spot was a marvel of atmospheric geometry, wait until you turn your gaze toward Saturn and witness a feature that seems less like a natural formation and more like a piece of cosmic engineering. Circling the planet's north pole is one of the most perfectly symmetrical and baffling patterns ever observed in our solar system, a gargantuan six-sided hexagon. This is not a trick of pixelation or a fleeting arrangement of clouds. It is a persistent, towering structure of winds, a jet stream shaped into the form of a geometric figure so precise it could have been drawn with a protractor. First glimpsed by the Voyager probes in the 1980s and later studied in breathtaking detail by the Cassini spacecraft, this hexagon has endured for at least 40 years and likely much longer, standing as a stable, rotating fixture in Saturn's turbulent atmosphere. Each of its 6 sides is longer than the diameter of Earth, making it a feature of almost incomprehensible scale. The winds along its sharp, defined edges race at speeds exceeding 200 miles per hour, creating a stark boundary between the stormy interior and the calmer atmosphere outside. It is a vast, swirling wall of cloud, a celestial honeycomb cell writ large across an entire polar region. The sheer existence of such a geometric shape in a chaotic fluid environment immediately pushes the boundaries of our understanding. How can a storm or any atmospheric system organize itself into a stable hexagon? The search for answers has led scientists not only to complex computer models but also back down to Earth, into laboratories where they can simulate planetary atmospheres in a tank. The key ingredient in these experiments is rotation. When a circular tank of fluid is rotated at different speeds between its center and its outer edge, something remarkable happens. Under the right conditions, the flowing fluid doesn't form vague, blobby patterns. It can snap into stable, polygonal shapes. Most commonly, a 6-sided hexagon emerges. This occurs because of the way waves organize themselves in a thin, rotating layer of fluid. The different speeds of rotation create what's known as a latitudinal shear flow, and this shear can trap certain types of waves called Rossby waves, forcing them to interfere with one another in a way that creates a standing wave pattern with sharp corners. In the lab, as the rotation speed increases, the fluid can transition from having no distinct shape to a circle, to a square, to a pentagon, and finally to a stable hexagon. This provides a powerful clue. Saturn's hexagon is likely a manifestation of a giant, planet-scale standing wave, pinned in place by the rotation of Saturn and the strong jet stream that flows around its north pole. But while the lab experiments give us a plausible mechanism, they also immediately highlight the profound mysteries that remain. The first is the staggering difference in scale. The hexagons created in laboratories are measured in inches. Saturn's hexagon is wider than 2 Earths, translating a small-scale fluid dynamics experiment to the atmosphere of a gas giant, with its immense pressures, complex chemistry, and deep, churning interior, is an enormous leap. The second, and perhaps greater, mystery is the hexagon's incredible longevity and stability. Laboratory fluid polygons are often transient, flickering in and out of existence as conditions change. Saturn's hexagon, however, has been a fixed feature for decades, rotating in sync with the planet's own deep internal rotation rate. It has survived seasons that last for over 7 years, enduring as the northern hemisphere moved from the darkness of winter into the light of summer. This suggests that the hexagon is not a superficial feature, but a deeply rooted expression of Saturn's fundamental atmospheric dynamics, possibly extending hundreds of kilometers down into the planet. This deep-rooted nature leads to another compelling layer of the puzzle. What is providing the energy to sustain this perfect shape against the dissipative forces of turbulence and friction? The answer may lie in the churning depths of Saturn itself. Just as with Jupiter, Saturn generates immense internal heat, believed to be a combination of primordial heat from its formation and the slow sinking of helium droplets through its liquid metallic hydrogen interior. This heat drives colossal convection currents, which in turn power the planet's ferocious jet streams. The hexagon appears to be a stable pattern carved into one of these powerful eastward-flowing jets. It acts as a barrier containing weather systems within its walls and creating a unique microclimate at the pole. Cassini's infrared and visible light cameras revealed complex, nested vortices and a massive hurricane-like storm spinning directly at the hexagon's center, a whirlpool of clouds that seems to be caged by the six-sided structure surrounding it. The final piece of this enigma is why the hexagon exists only at the North Pole. Cassini arrived during Saturn's northern winter, when the South Pole was also visible, and no similar permanent hexagon was found there. Instead, the South Pole featured a massive, swirling vortex with eye walls, but no geometric edges. This asymmetry tells us that the conditions that give rise to the hexagon, the precise speed and depth of the jet stream, the atmospheric temperature gradients, or perhaps even the influence of Saturn's peculiar magnetic field are unique to the Northern Hemisphere. It suggests that the planet's two poles are not identical twins, but rather fraternal ones, each with its own distinct atmospheric personality shaped by subtle differences in their underlying dynamics. The enduring presence of Saturn's north polar hexagon is a humbling reminder that the physics of fluid dynamics, even on a scale we can replicate in a lab, can produce results of breathtaking beauty and complexity when unleashed upon a planetary stage. It stands as a celestial monument to the unseen waves and forces that sculpt the atmospheres of giants, a six-sided signature written in the clouds waiting for us to fully decipher its meaning. After witnessing the serene, geometric perfection of Saturn's hexagon, we now travel inward, back toward Earth, to confront a day when the sky itself exploded with the force of a nuclear weapon. On the morning of June 30th, 1908, in a remote and largely uninhabited part of Siberia near the Podkamennaya Tunguska River, a brilliant fireball streaked across the sky, outshining the sun. Moments later, a blast of unimaginable force ripped through the atmosphere. The shock wave was so powerful that it flattened an estimated 80 million trees across 2,000 square kilometers of dense forest, radiating outward from a central point in a stunning butterfly wing pattern of destruction. The seismic shudder was recorded as far away as England. In nearby villages, people were thrown from their feet and windows were shattered hundreds of kilometers away. For nights afterwards, skies across Europe and Asia glowed so brightly that you could reportedly read a newspaper at midnight. This was the Tunguska event, the largest impact event in recorded human history, and yet, over a century later, it remains a profound scientific enigma because of one glaring missing piece: there is no crater. The conventional and most widely accepted explanation is that a small asteroid or comet, roughly 50 to 60 meters across, entered Earth's atmosphere at a tremendous speed of perhaps 30,000 miles per hour. But it never reached the ground. Instead, the immense pressure and heat generated during its descent caused it to explode in a massive airburst several kilometers above the surface. This kind of detonation, releasing energy equivalent to 10 to 15 million tons of TNT, focuses the entire destructive force of the object downward in a single, devastating shock wave, much like setting off a bomb in midair. This cleanly explains the radial pattern of flattened trees and the absence of a traditional impact crater. Expeditions to the site, the first of which wasn't until the 1920s, led by the determined scientist Leonid Kulik, found the ground littered with scorched, branchless tree trunks, all pointing away from the epicenter, but no significant fragments of the impacting body and no smoking gun of a crater. This is where the mystery deepens from a simple historical account into an active scientific puzzle. An airburst makes sense, but the specifics of this one are strangely unique. First, there is the perplexing lack of any substantial meteoritic debris. While tiny, glassy spherules of fused rock have been found in the soil, believed to be remnants of the vaporized object, no large chunks have ever been recovered. This points strongly toward the object being a fragile, icy comet rather than a stony asteroid, as a comet would have disintegrated more completely. Yet this leads to the second major anomaly, the calculated trajectory. Studies of the tree fall patterns suggest the object approached at a remarkably shallow angle, perhaps only 10 to 15 degrees above the horizon, and from roughly the east-southeast. This is an unusually shallow entry for such a destructive event. Most large impactors, like the one that created Meteor Crater in Arizona, come in on much steeper trajectories. A shallow path means the object spent a much longer time and distance traveling through the dense lower atmosphere, which should have caused a weaker, more dispersed fragmentation rather than a single, concentrated explosion. The fact that it still produced such a focused, immensely powerful airburst suggests the object possessed a strange and particular combination of strength and fragility that we still don't fully understand. The unusual nature of the event has, understandably, given rise to more exotic explanations over the decades, ideas that, while lacking mainstream evidence, persist due to the lingering questions. One of the most captivating is the suggestion that Earth was struck by a tiny, primordial black hole. The theory proposes that a black hole with the mass of a large asteroid, but only the size of an atom, could have passed straight through the Earth. It would have entered the atmosphere, created a shock wave mimicking an airburst as it compressed the air in front of it, and exited out the other side of the planet into the North Atlantic, leaving no crater and no debris. While a fascinating exercise in theoretical physics, there is no evidence for such an exit event, and the concept remains firmly in the realm of speculation. Another fringe theory involves a chunk of antimatter, perhaps a piece of an antimatter asteroid, annihilating upon contact with our normal matter atmosphere in a spectacular release of pure energy. This, too, would leave no debris. However, astronomers have found no evidence for large accumulations of antimatter in our solar system, and such an event would be expected to produce a specific signature of gamma radiation that was not observed. The true, enduring significance of Tunguska, therefore, lies not in fringe theories but in the sobering scientific reality it represents. This was not a one-in-a-billion-year fluke. It was a dramatic reminder of our planet's vulnerability. Objects of this size are estimated to hit Earth every few hundred to every 1,000 years. If the Tunguska object had arrived just a few hours later, its path would have brought it over the major population centers of Europe, resulting in a cataclysm of unimaginable proportions. The event serves as the foundational case study for the modern field of planetary defense, forcing us to acknowledge that the cosmic shooting gallery is real and that our atmosphere provides only a partial shield. The central puzzle, why this particular object behaved in such a uniquely destructive way, drives ongoing research into the composition and structural integrity of near-Earth objects. Was it a porous rubble pile asteroid that flew apart in just the right way? A dormant comet nucleus that shattered like glass? Each new asteroid we study up close, each new comet we visit, adds a piece to this century-old puzzle, a silent warning from the Siberian taiga written in fallen trees. Yet, for all the violence and drama we've witnessed within the inner solar system, nothing prepares us for the quiet, deep space mystery that lies at the very fringe of the Sun's influence. Far beyond the orbit of Neptune, in the cold, dark realm where sunlight is a faint, lonely star, exists a vast reservoir of icy worlds known as the Kuiper Belt. Think of it as a far more expansive and massive cousin to the asteroid belt, a donut-shaped region populated by frozen remnants from the solar system's birth. For decades, astronomers predicted that this belt of icy bodies would extend outward in a relatively smooth and gradual distribution, with the number of objects slowly thinning out the farther you go, eventually blending into the emptiness of interstellar space. But when we finally developed the telescopes capable to peer into this deep freeze and conduct a cosmic census, we encountered something utterly baffling. Instead of a gentle decline, the population of Kuiper belt objects plummets off a cliff. At a distance of roughly 50 astronomical units from the Sun, that's 50 times the Earth-Sun distance, the number of detectable objects drops so dramatically and suddenly that it's as if someone built a celestial wall out in the darkness. This is the Kuiper Cliff, and its existence challenges our most fundamental stories of how the solar system formed and what might still be lurking in its uncharted territories. This sharp boundary is a profound anomaly because our standard models of planetary formation paint a very different picture. In the classic view, the early solar system was a swirling disk of gas and dust around the young sun. The planets coalesced from this material, but beyond the giants, a vast ring of icy planetesimals was left behind. Over billions of years, the gravitational nudges from Neptune are thought to have sculpted this population, scattering some objects inward and pushing others into more distant, stable orbits. These models consistently produce a Kuiper belt that fades away gradually over a much larger distance, perhaps out to 1,000 astronomical units or more. The observed cliff, however, is stark and abrupt. It's like taking a demographic survey of a city and finding neighborhoods with bustling populations right up to a specific street, and then beyond that line, almost complete emptiness. This isn't just a minor discrepancy, it's a sign that a major piece of our solar system's history is missing from the Chinese letter. Something powerful and decisive must have acted like a cosmic gardener, shearing off the outer edge of this icy reservoir. One of the most thrilling hypotheses proposed to explain this cliff involves a hidden world. Not a small one either. Astronomers have speculated that an unseen, perhaps Earth-sized or even Mars-sized planetary body could be orbiting the Sun far beyond Neptune. This potential Planet 9 or similar distant perturber would have a gravitational influence vast enough to have reshaped the outer Kuiper belt billions of years ago. The theory suggests that during the solar system's tumultuous youth, this unseen planet's gravity acted like a shepherd, gravitationally scattering many of the icy objects in its vicinity. It would have flung some of them inward toward the region we now observe as the populated part of the Kuiper belt, while ejecting others entirely from the solar system. This process would have effectively cleared out a vast swath of space beyond its own orbit, creating the very population drop-off we see today. The cliff, in this scenario, is the enduring signature of this ancient clearing event, a fossilized boundary marking the edge of this hidden planet's domain. The search for this theoretical world is ongoing, a modern-day celestial detective story that involves tracing the peculiar, clustered orbits of the most distant Kuiper belt objects we can find, looking for the subtle gravitational fingerprint of the unseen shepherd that herds them. However, an equally compelling and entirely different explanation looks not to a hidden planet but to the Sun's very origins. Our star was not born in isolation. It likely formed within a dense cluster of hundreds or even thousands of other sibling stars, all packed relatively close together for a few million years before gradually drifting apart. In such a crowded stellar nursery, close encounters between stars would have been common. Imagine a scenario where another young star, perhaps a sibling of our Sun, passed relatively close to our infant solar system. The gravitational pull from this interloper would have been catastrophic for the outer solar system. It could have ripped away a huge portion of the primordial Kuiper belt, stripping the icy bodies from the Sun's grasp and hurling them into interstellar space. This stellar flyby would have effectively lopped off the outer reaches of the disk, leaving behind the truncated belt with its sharp edge that we find so puzzling today. This theory elegantly explains the cliff without requiring a new planet, framing our solar system not as an isolated fortress, but as a survivor of a dynamic and crowded early environment. The Kuiper Cliff, then, becomes a permanent scar from a traumatic close encounter that happened over 4 billion years ago. Deciding between these two theories, or perhaps a combination of both, is an active frontier of astronomy. Each has its strengths and its challenges. The hidden planet model is powerful, but it requires the existence of a substantial world that has so far eluded every search. The passing star hypothesis is dramatic and plausible given what we know about star formation, but it requires the flyby to have occurred at just the right distance and angle to sculpt the belt we see without completely disrupting the orbits of the giant planets. There are even other, more subtle possibilities, such as the slow, grinding effects of gravitational resonances within the disk of icy objects themselves, or the possibility that the original protoplanetary disk of gas and dust from which the solar system formed had its own sharp outer edge imprinted at birth. Unraveling this mystery requires more than just theory. It requires deeper surveys of the sky. Every new, distant Kuiper belt object we discover, especially those that lie right on the edge of the cliff or beyond it, provides another crucial data point. Their orbits are clues, and by mapping them with increasing precision, we are slowly piecing together the gravitational history of the solar system's final frontier. The Kuiper Cliff is a silent reminder that even in the most remote and seemingly empty quarters of our cosmic neighborhood, the echoes of dramatic events from the dawn of time are still waiting to be heard. But what lies beyond even the stark boundary of the Kuiper Cliff? Our journey now takes us to the ultimate frontier of our solar system, a realm so distant and faint that it exists only as a brilliant piece of theoretical deduction. This is the Oort cloud, a vast spherical shell of icy planetesimals believed to encase our entire planetary system like a colossal, gossamer-thin bubble. Its scale is almost impossible to grasp. While the Kuiper belt extends out to about 50 astronomical units, the inner edge of the Oort cloud is thought to begin roughly 2,000 astronomical units from the Sun, and its outer boundary may stretch to a mind-numbing 100,000 astronomical units, nearly halfway to the next closest star. This makes it the single largest structure in our solar system, yet we have never directly observed a single object within it. Its entire existence is a ghostly presence inferred from the most ethereal of messengers, long-period comets. These comets are the key to the mystery. Occasionally, a pristine ball of ice and rock, a long-period comet, will fall into the inner solar system from a random direction in the sky, not from the flat plane of the planets, but from any point on the celestial sphere. Comets like Hale-Bopp or the recent comet Neowise follow immense elliptical orbits that take them tens of thousands of years to complete a single journey around the Sun. Their random arrival directions are the crucial clue. If all cometary material originated in the flat disk of the early solar system, we would expect these visitors to arrive roughly along the ecliptic plane, just as short-period comets from the Kuiper belt do. The fact that they come from everywhere points to a vast spherical reservoir surrounding us, a shell from which gravitational nudges from passing stars or the galactic tide can occasionally dislodge an object, sending it on a million-year fall toward our Sun. The profound mystery of the Oort cloud is not just that it exists, but how it formed. How did trillions of icy objects end up so impossibly far from the Sun, arranged in a three-dimensional shell? The leading theory paints a picture of cosmic billiards on a grand scale. In the solar system's violent infancy, the newly formed giant planets Jupiter, Saturn, Uranus, and Neptune acted as gravitational titans, shaking up the orbital architecture of the countless smaller bodies around them. As these planets migrated and settled into their current orbits, their immense gravity would have flung surrounding planetesimals outward in all directions. Some of these ice dwarfs and comet-like bodies were ejected entirely, becoming rogue objects drifting in interstellar space. but a significant fraction were thrown out with just enough energy to escape the planet's immediate vicinity, but not enough to break free from the Sun's gravity altogether. They sailed out to the farthest reaches of its gravitational influence, where they now reside in a state of delicate balance, their orbits slowed to a near standstill by the incredible distance. However, this elegant model runs into a significant problem when trying to create the perfectly spherical distribution we infer from the comets. Computer simulations show that the scattering process from the giant planets, acting from within a flat disk, tends to produce a somewhat flattened cloud, more of a thick disk than a true sphere. So, what force sculpted this disk into the immense, round shell we believe exists today? Astronomers point to the environment of the Sun's birth. Our star was not born in isolation, but within a dense cluster of perhaps thousands of sibling stars, all packed relatively close together for the first few 100 million years. During this time, close encounters with these neighboring stars would have been frequent. The gravitational pull from a passing star would have been weak at such vast distances, but over millions of years, these gentle tugs could have effectively randomized the orbits of the outermost icy bodies, pulling them out of the flat plane and perturbing them into the spherical distribution we see evidence for today. The galactic tide, the subtle gravitational gradient created by the Milky Way galaxy as a whole, may have also played a role over billions of years, further shaping this distant cloud. The Oort cloud, therefore, is more than just a freezer for comets. It is a frozen archive of the solar system's earliest social interactions. Its very shape may be a fossilized record of the stellar neighborhood our Sun grew up in, a permanent imprint of the gravitational pushes and pulls from long-lost sibling stars. Its existence also hints at a vast population of objects we have yet to dream of, a hidden kingdom of ice in the profound darkness. Every long-period comet that graces our skies is a refugee from this unimaginably remote frontier, a tiny, melting sample from the very edge of the Sun's domain, reminding us that our solar system's influence extends into a void far greater and more mysterious than we can directly see. But for every silent mystery written in rock and ice, there is one that arrived as a shout, a single, deafening blast of radio noise that has echoed through the decades as the ultimate cosmic what if. It was a quiet summer evening on August 15, 1977, at the Big Ear Radio Telescope in Ohio. This massive instrument, part of the search for extraterrestrial intelligence, or SETI, was methodically scanning the sky, listening for any signal that stood out from the natural hiss of the universe. The system worked by printing reams of data, long sequences of numbers and letters representing signal strength. For the most part, it was monotonous work, a vigil of silence. But on this night, something extraordinary happened. As the telescope's gaze passed near the constellation Sagittarius, the receiver was jolted by an intense, focused burst of radio waves. The signal was so powerful that it maxed out the equipment's scale. When volunteer astronomer Jerry Amon reviewed the data printout the next day, he was so stunned by the string of characters 6-5 that he circled the sequence and scrawled a single, now legendary word in the margin: wow. What made this 72-second signal so remarkable wasn't its duration, but its nearly perfect profile. It possessed all the hallmarks of a signal that SETI researchers had theorized would indicate an artificial extraterrestrial origin. First, it was a narrowband signal concentrated on one specific frequency, the hydrogen line at 1420 MHz. This is a scientifically significant frequency, the natural emission line of the most common element in the universe, and a logical watering hole where advanced civilizations might choose to broadcast. Natural cosmic objects like stars or nebulae emit radio noise across a wide range of frequencies. This was a sharp, precise whistle, not the roar of static. Second, the signal's intensity rose and then fell in a perfect curve over the 72 seconds. matching exactly what you would expect as the stationary Big Ear telescope's fixed beam slowly drifted across a point-like source in the sky. It appeared, peaked, and then vanished with a beautiful, predictable symmetry. It came from a region of space with no known stars or planets, suggesting an origin far beyond our solar system. In that brief window, it seemed we might have just overheard a cosmic conversation. The immediate and obvious next step was to listen again. If this was a deliberate beacon or even an accidental leak of radiation from an alien civilization, it should be there when we pointed our telescopes back at that same spot. And so began a quest that has now lasted for over 4 decades. Astronomers have repeatedly trained some of the world's most powerful radio dishes, including the Very Large Array, toward the WOW signal's coordinates. They have scanned that patch of sky for thousands of hours, listening for a repeat, for an echo, for anything. The result has been a profound and enduring silence. Not a single chirp, not a hint of a signal has ever been detected again from that location. This complete lack of a repeat performance is in many ways as baffling as the original signal itself. If it was a message, why was it sent only once? If it was a beacon, why did it fall silent? The mystery only deepens with time. The compelling nature of the signal has, of course, spurred a relentless search for a more conventional, natural explanation. One of the most discussed theories emerged in 2017, proposing that the signal could have been caused by a hydrogen cloud surrounding a passing comet. The idea was that 2 specific comets, which happened to be in that region of the sky at the time, could have emitted a burst of radio energy at the right frequency. It was an elegant solution, but it quickly unraveled under scrutiny. For one, these comets were not actually in the telescope's beam at the precise moment of the detection. Furthermore, comets are known to emit radio waves across a broad spectrum, not in the intensely narrow, focused band that characterized the WOW signal. The scientific consensus is that a comet simply could not produce a signal with such a specific and artificial-looking profile. Other natural possibilities have been explored and largely dismissed. It wasn't a reflection of a human-made signal bouncing off a piece of space debris, as our own terrestrial transmissions have a different, recognizable fingerprint. It wasn't a secret military satellite or a spy transmission, as no known human technology of the era matched the signal's unique characteristics. The possibility of a software glitch or an equipment malfunction has also been considered, but the Big Ear telescope was functioning perfectly before and after the event, and no other anomalous readings were recorded. Every proposed natural explanation seems to hit a wall, failing to account for one or more of the signal's perfect, puzzling attributes. So where does that leave us? The WOW signal endures as the great white whale of SETI, a solitary data point that is both too perfect to ignore and too isolated to verify. It represents the ultimate tease, a glimpse of a possibility that hangs forever unconfirmed in the vastness of space. It taught us that the cosmos is capable of producing surprises that fit our most hopeful models for contact, while also teaching a harsh lesson in cosmic patience and probability. Perhaps it was a one-time event, the catastrophic explosion of an alien civilization's power grid, or a beacon that swept past Earth only once in a million-year cycle. Maybe it was a message intended for someone else, and we simply happened to be in the way. Its legacy is not an answer, but a permanent question mark, a reminder that in the grand search for company in the universe, a single, powerful WOW can be both a beginning and an end, fueling our imagination and our scientific rigor in equal measure for generations to come, leaving behind the tantalizing silence of the WOW signal. We turn our focus to a mystery that unfolded not with a bang, but with a whisper, a subtle, persistent tug on 2 robotic explorers as they ventured into the abyss. This is the story of the Pioneer anomaly. Launched in the early 1970s, Pioneer 10 and 11 were true trailblazers, Pioneer 10 was the first spacecraft to travel through the asteroid belt and make close-up observations of Jupiter, while Pioneer 11 went on to achieve humanity's first encounter with Saturn. After completing their planetary missions, both spacecraft continued on trajectories that would eventually carry them out of the solar system entirely, becoming silent ambassadors drifting among the stars. For decades, scientists at NASA, a jet propulsion laboratory, meticulously tracked their positions using the Deep Space Network, relying on the precise Doppler shift of their radio signals to measure their velocity and distance with incredible accuracy. And that's when they noticed something was off. As the twin probes journeyed beyond the orbit of Pluto, navigators discovered that both were ever so slightly off course. They were not quite where our best gravitational models predicted they should be. Both Pioneers were experiencing a minuscule, unplanned, and constant acceleration back toward the Sun. This wasn't a sudden jerk or a dramatic change in velocity. It was a tiny, persistent push, equivalent to just 10 billion times weaker than the gravity we feel at Earth's surface. To put that in perspective, this force was so small that its effect was like slowing down the spacecraft by a single inch per second every day. For most missions, such a minuscule discrepancy would be lost in the noise, negligible and unremarkable. But the Pioneers were on a one-way trip to interstellar space, and over the vast distances and years of travel, this tiny, unaccounted-for force accumulated into a significant navigational drift, a discrepancy that grew to thousands of kilometers. The laws of physics, as we understood them, provided no explanation. There was no hidden planet pulling them back, no mysterious drag from the interstellar medium. It was as if space itself was applying a gentle, invisible brake. This tiny anomaly ignited a massive debate within the physics community that lasted for over 2 decades. Could this be the first tangible evidence of a flaw in Einstein's theory of general relativity? Some theorists proposed exotic explanations, suggesting that the anomaly might be a signature of dark matter exerting a gravitational pull in the outer solar system, or perhaps evidence for new physics, like modifications to the law of gravity itself on very large scales. The idea that our fundamental understanding of gravity might be incomplete was electrifying. For a time, the Pioneer anomaly represented a potential crack in the foundation of modern physics, a hint that our cosmic rulebook needed a serious revision. The real answer, however, turned out to be a masterclass in engineering humility and the power of relentless detective work. A small group of researchers, led by the determined physicist Slava Turyshev, refused to let the mystery rest. They embarked on a monumental effort to recover the original data from decades-old magnetic tapes and archaic computer formats, and then painstakingly built a computer model of the Pioneer spacecraft down to the most minute detail. Their breakthrough came when they realized they had been overlooking a very mundane but incredibly subtle source of propulsion: heat. The Pioneers were powered by radioisotope thermoelectric generators, or RTG. These devices convert the heat from the natural radioactive decay of plutonium-238 directly into electricity. This process also makes the RTGs incredibly hot, glowing with a temperature of hundreds of degrees. The spacecraft themselves were designed with a specific geometry, spinning slowly to maintain stability. The team's new, exquisitely detailed model revealed that this heat wasn't radiating away from the spacecraft uniformly in all directions. More heat was being emitted from the back of the spacecraft's main dish antenna, which was pointed toward Earth, than from the front. Why does this matter? In physics, every action has an equal and opposite reaction. Photons of heat radiation carry a tiny amount of momentum. If more infrared photons are pushing off from the back of the spacecraft than from the front, the net effect is a tiny but continuous force pushing the craft backward toward the Sun. It's a phenomenon known as anisotropic thermal radiation. Think of it like a very, very faint rocket engine where the exhaust is nothing but invisible heat. This recoil from the lopsided heat signature was precisely the mysterious sunward acceleration that had baffled scientists for so long. When Turyshev's team factored this thermal recoil force into their models, the vast majority of the Pioneer anomaly simply vanished. The spacecraft were behaving exactly as they should, propelled by the gentle, unseen pressure of their own waste heat. Yet even with this brilliant resolution, a ghost of the anomaly remains. After accounting for the anisotropic heat radiation with our best available data, a tiny residual acceleration persists, a whisper of a signal so small it sits right on the edge of our measurement capabilities. This lingering discrepancy could still be an unmodeled effect, perhaps a subtlety in the way heat radiated from the spacecraft's louvered vents or a tiny error in our data. But its continued presence serves as a powerful and humbling reminder. The Pioneer anomaly shows us that when we push our instruments to the limit of their precision at the very frontier of our solar system, we enter a realm where even the most mundane physical effects, the gentle push of a photon, the uneven glow of a warm surface, can masquerade as revolutionary new physics. It underscores that our search for the profound often begins with a deep and meticulous understanding of the ordinary, and that the universe still holds subtleties so fine we have only just begun to measure them. After chasing whispers of heat and phantom forces within our own solar system, we now cast our gaze much farther out, to a star that single-handedly resurrected one of science fiction's most ambitious dreams. Over 1,000 light-years away, in the constellation Cygnus, lies a seemingly ordinary star named KIC 8462852, now far better known as Tabby's star, after the astronomer Tabitha Boyajian, who first brought its strangeness to the world. It was monitored for years by the Kepler Space Telescope, an instrument designed to hunt for planets by detecting the tiny, periodic dips in starlight caused when an alien world transits or passes in front of its sun. Most stars in Kepler's view showed these predictable, repeating dimming patterns, but Tabby's star was different. It was a cosmic rebel, a star whose light did not behave like any other. The anomalies began with staggering, irregular drops in brightness. We're not talking about the gentle 1% dimming caused by a Jupiter-sized planet. Tabby's star experienced plunges of up to 22%, a colossal dimming that suggested something enormous was blocking its light. Even more baffling was the pattern, or rather, the lack of one. The dips were not periodic, they were chaotic. They would last for days, sometimes weeks, with no discernible rhythm. One major event saw the star's light plummet by a huge margin, stay dim for over a week, and then slowly recover. It was as if someone, or something, was randomly throwing a series of vast, opaque curtains in front of the star, a light show of shadows that defied every conventional explanation. In the face of such profound weirdness, it's no surprise that the most sensational hypothesis erupted into the public consciousness: the idea of an alien megastructure. Specifically, theorists proposed a concept straight from the pages of hard science fiction, a Dyson swarm. The idea, first articulated by physicist Freeman Dyson, is that a civilization vastly more advanced than our own might eventually need to capture the entire energy output of its star. They would construct a vast array of energy-collecting satellites, a swarm of millions or billions of individual constructs orbiting their sun, gradually blocking more and more of its light from view. The irregular, deep dimming of Tabby's star seemed at first blush to be a perfect, if startling, match for such a structure. Perhaps we were witnessing a Dyson swarm under construction, with massive panels and platforms being moved into place, creating a random, clumpy pattern as they orbited. It was a hypothesis that captured the imagination of the entire world, turning an obscure star catalog number into a global sensation and a symbol of humanity's deepest cosmic question: are we alone? Yet, extraordinary claims demand rigorous scrutiny, and the scientific community quickly set to work finding natural explanations, each of which is as strange in its own right as the alien hypothesis. The most compelling evidence now points away from solid megastructures and toward a colossal cloud of dust. Detailed follow-up observations revealed a crucial clue. The star dimmed more in some wavelengths of light, like blue and ultraviolet, than in others, like infrared. This is a classic signature of dust. Tiny dust particles are better at scattering and blocking shorter, bluer wavelengths while allowing longer, redder light to pass through more easily. If the obscuring object were a solid structure, like a planet or a giant metal panel, it would block all wavelengths of light equally. The fact that the dimming is chromatic or color-dependent strongly suggests we are looking at a vast, opaque cloud of fine, micron-sized dust grains. So, what could create such an immense and chaotic dust cloud? One leading theory is one of almost unimaginable cosmic violence, the recent destruction of a planet or moon. Imagine a catastrophic collision within the star system, a planetary smash-up so powerful that it shattered a world into trillions of fragments. The resulting debris field, a chaotic swarm of dust, rock, and vapor, would orbit the star in a highly irregular, clumpy torus. As these dense clouds of debris pass in front of Tabby's star from our vantage point, they would cause the dramatic, aperiodic dimming we observe. This scenario explains the deep dips and the lack of a clear period, as the debris would be spread across a wide range of orbits. Another plausible, though still exotic, idea involves a family of giant, disintegrating comets. We're not talking about typical comets from our solar system, but rather a swarm of colossal, icy bodies, perhaps hundreds of kilometers across, on long, eccentric orbits. As they swing close to their star, the intense heat could cause them to violently outgas and break apart, releasing enormous clouds of dust and gas that would temporarily blot out the star's light. A whole family of such giant comets, each disintegrating at different times, could create the erratic dimming pattern. Despite these compelling natural theories, the ultimate mystery of Tabby's star is far from solved. The sheer scale of the dimming remains difficult to fully explain. Generating enough dust to block 22% of a star's light requires the destruction of an almost unbelievable amount of material. Furthermore, long-term studies have revealed another, slower and more perplexing trend. The star's overall brightness appears to be very slowly but steadily fading over decades, a phenomenon separate from the sharp dips. This long-term dimming adds yet another layer of complexity, suggesting a process that is both ongoing and deeply woven into the star's environment. The alien megastructure hypothesis, while now considered a distant long shot, played a vital role. It ignited public interest and, more importantly, it spurred a new era of intense, multi-wavelength scrutiny of this strange star. It demonstrated that by being bold enough to consider even the most fantastic possibilities, we push ourselves to collect better data and to question our assumptions more deeply. Tabby's star stands as a permanent monument to cosmic curiosity, a reminder that our galaxy is still capable of producing phenomena that challenge our categories and force us to look at the familiar machinery of star systems in a completely new light. From the chaotic flickering of a distant sun, we now turn to a spectacle of cosmic symmetry so perfect it seems almost artificial, a structure that appears less like a nebula and more like a celestial cathedral built from light and dust. Officially known as a protoplanetary nebula, a fleeting phase in the life of a sun-like star, the object surrounding the star HD 44179 is far better known by its evocative nickname, the Red Rectangle. And it is a name that fits perfectly. When viewed through powerful telescopes, this nebula doesn't present the soft, ethereal glow of the Orion Nebula or the intricate, shell-like filaments of a supernova remnant. Instead, it forms a stark, geometric shape, a vivid, blood-red rectangle with a distinct X-shaped structure at its core, as if two luminous cones have been pushed through each other at the center, creating a framework of sharp, opposing lines. It is a sight so unusual and so precise that it feels deliberately constructed, a piece of cosmic art hanging in the void about 2,300 light-years away. The true mystery of the red rectangle, however, is not merely its shape but the very nature of its light. When astronomers break its crimson glow down into a spectrum, spreading its light out into a rainbow to analyze its chemical composition, they encounter something profoundly strange. Instead of the expected sharp, dark absorption lines or bright emission lines that act as fingerprints for specific elements like hydrogen, helium, or oxygen, the spectrum of the red rectangle is dominated by a broad, smooth, and completely featureless hum of red light. This phenomenon is known as extended red emission, or AIR, and it represents one of the most stubborn puzzles in the entire field of astrophysical spectroscopy. A featureless spectrum is the scientific equivalent of a blank face. It offers no easy clues. It tells us that whatever is producing this light is not a simple gas being excited or a familiar dust grain scattering starlight. The process is something far more exotic, a form of luminescence that we have yet to fully replicate or understand in our laboratories here on Earth. So, what could possibly be causing this mysterious broad red glow? The prime suspect in this cosmic detective story is carbon, but not in any simple, elementary form. The leading theory points to the existence of complex organic molecules, vast networks of carbon and hydrogen atoms known as polycyclic aromatic hydrocarbons, or PAHs for short. These are essentially tiny, flake-like fragments of graphite. Think of them as nano-sized soot particles. Under the intense ultraviolet radiation from the central star, these pH molecules can become energized and then re-emit light as they calm down, a process known as fluorescence. And while pHs are known to produce specific infrared signatures, the broad, smooth nature of the air suggests we might be dealing with a more complex version of this process, perhaps involving a rich soup of many different types of pHs, all glowing at slightly different wavelengths, their individual signals blending together to create that smooth, red hum we observe. It's as if the nebula is filled with the smoldering embers of a trillion microscopic campfires, all burning with the same strange, ruddy light. An even more intriguing possibility involves a concept borrowed from cutting-edge materials science on Earth: quantum dots. These are nanometer-sized crystals of semiconductor material whose optical properties are dictated not by their chemistry alone, but by their physical size. Change the size of the dot by just a few atoms, and you change the color of light it emits. In the red rectangle, the prevailing thought is that we might be seeing the glow of carbon-based quantum dots, tiny cages of carbon atoms, perhaps even fragments of diamonds or other exotic forms of carbon, forming in the dense, dusty outflow from the dying star. The relentless stellar wind and intense radiation field could be processing simple carbon compounds, forging them into these advanced nanostructures. If this is correct, then the extended red emission is the collective glow of countless quintillions of these microscopic diamonds, all tuned to emit the same deep red light, a celestial display of nanotechnology on an astronomical scale. Yet, for all the elegance of these theories, the definitive proof remains elusive. The exact size, structure, and composition of the particles responsible for the air are still unknown. Is it a uniform population of one specific type of quantum dot, or a diverse zoo of different carbon-based macromolecules? Furthermore, the red rectangle's iconic shape adds another layer to the mystery. The stark X pattern is believed to be caused by two powerful, opposing jets of material being ejected from the star's poles, while a thick, dense disk of dust girdles its equator, pinching the outflowing gas into the distinct conical lobes that form the rectangle. This intricate geometry acts like a laboratory beaker, concentrating the chemical processes that create the mysterious red-emitting material in specific regions. The nebula, therefore, is not just a pretty picture, it is a dynamic chemical factory, and the air is the signature of its most enigmatic product. This cosmic structure challenges our understanding of how complex matter forms in the harsh environment of space. suggesting that the death throes of stars may be far more chemically creative than we ever imagined, forging not just new elements, but entirely new forms of material that paint the cosmos in colors we are still learning to see. We now venture to the outer reaches of Saturn's magnificent kingdom, to a world that seems to defy its own identity. Meet Iapetus, the solar system's most striking example of split personality. This mid-sized moon presents a cosmic riddle painted in the starkest black and white imaginable. One hemisphere, its leading face in its orbit around Saturn, is darker than fresh asphalt, a landscape of deep charcoal gray. The other, trailing hemisphere, gleams with the brilliant reflectivity of freshly fallen snow. From a distance, it looks less like a natural satellite and more like a celestial yin-yang symbol, a perfect sphere divided into light and dark. The boundary between these two realms is razor-sharp, a transition so abrupt it seems almost artificial, as if a giant cosmic brushstroke painted one half of the moon a deep, forbidding shade. This stark duality is unlike anything else we see among the hundreds of moons in our solar system, and it points to a fascinating interplay of external forces and internal self-amplification. The initial clue to this mystery comes from Iapetus's unique orbital position and a bit of cosmic sibling rivalry. Iapetus orbits relatively far from Saturn, but inside its path circles a much more distant and peculiar moon named Phoebe. Phoebe is a dark, captured object, likely a former denizen of the Kuiper belt, and it travels in a retrograde orbit, meaning it moves in the opposite direction to Saturn's rotation and the orbits of its inner moons. This backward journey is critically important. Phoebe is constantly being pelted by micrometeorites, which kick up a fine, dark dust from its surface. Because Phoebe is orbiting backwards, this cloud of dust doesn't drift inward smoothly. Instead, it drifts sunward, moving against the flow of traffic, so to speak. As Iapetus plows forward on its own orbit, its leading hemisphere continually rams into this inward-falling stream of dark Phoebe dust. Think of a car driving through a swarm of insects. The front windshield gets splattered, while the rear window remains relatively clean. This simple, elegant process provides the initial stain, the first layer of soot that begins to darken one entire face of Iapetus. But this external coating is only the beginning of the story. If the process stopped there, we might expect Iapetus to be merely dusty on one side. Instead, we see an extreme contrast that has been dramatically enhanced over time by a powerful, self-reinforcing feedback loop known as thermal segregation. Here's how this ingenious process works. The initial sprinkling of dark dust from Phoebe changes the moon's albedo, which is a measure of how much sunlight it reflects. The dark dust, being much less reflective, absorbs a significantly greater amount of solar energy. This causes the temperature on the darkened regions to rise. On a world like Iapetus, which is composed largely of water ice, this slight warming is enough to trigger a profound change. The water ice on the surface of the dark areas begins to sublimate, that is, it turns directly from solid ice into water vapor without ever becoming a liquid. This is where the runaway effect kicks into high gear. The water vapor now lifting off the warm, dark terrain doesn't just disappear into space. It drifts across the surface until it reaches a colder area. And where are the coldest areas? They are the bright, still pristine icy regions on the trailing hemisphere and at the poles, which efficiently reflect sunlight and therefore remain frigid. When the water vapor encounters these cold traps, it immediately recondenses, freezing directly back into solid, bright white frost. This process does two things simultaneously. It further darkens the originally stained areas by removing their bright surface ice and leaving behind an even more concentrated layer of dark dust, which makes those areas absorb even more heat and sublimate even more ice. At the same time, it makes the bright areas even brighter and colder by depositing a fresh, clean layer of frost, which makes them even more effective at reflecting heat and attracting more vapor. It's a perfect self-perpetuating cycle. The dark gets darker and warmer, the bright gets brighter and colder, and the stark divide between them sharpens with every passing eon. This remarkable process explains why the contrast on Iapetus is so much more extreme than on any other moon that might also be dusted with foreign material. Thermal segregation took a simple initial condition, a sprinkling of dark dust, and amplified it into a global phenomenon. It transformed a slight blemish into a fundamental characteristic of the world. The lingering mystery is why this hasn't happened elsewhere. Many icy moons are subject to dusty debris, but none exhibit this dramatic bipolar personality. The answer may lie in Iapetus's specific combination of a slow rotation period. It takes 79 Earth days to spin once, and its considerable distance from Saturn. The long day allows for prolonged heating and cooling cycles, while the great distance means Saturn's reflected light and heat, which can moderate temperatures on closer moons like Enceladus, is too weak to interrupt the delicate thermal segregation process. Iapetus exists in a perfect, lonely sweet spot where this runaway feedback could operate undisturbed for billions of years, creating a visual masterpiece of cosmic contrast that stands as a stunning testament to how small initial imbalances can, through the patient work of physics, sculpt a world into a work of art. But just as Saturn's hexagon demonstrates geometric perfection on a planetary scale, its magnificent ring system holds a mystery that is both ethereal and transient. In the broad, dense expanse of the planet's B-ring, astronomers have observed fleeting, ghostly features that appear like phantom brushstrokes against the dark canvas of space. These are the enigmatic spokes, radial, shadowy streaks that stretch across thousands of kilometers, appearing suddenly and then fading away over just a few hours. They were first glimpsed by the Voyager probes in the early 1980s, and many scientists at the time thought they might be a rare, one-off phenomenon. But decades later, when the Cassini spacecraft arrived for its long-term study of Saturn, it confirmed that the spokes were not only real, but a regular, repeating feature of the ring system, appearing most frequently when the rings are tilted edge onto the Sun during Saturn's equinox. Watching them form and dissipate is like watching a celestial shadow play, where the actors are invisible and the script is written in the language of electromagnetic forces. What makes these features so puzzling is their behavior and composition. The spokes are not solid structures or physical gaps in the rings. Instead, they are vast collections of exceptionally fine, microscopic dust particles that have somehow become levitated above and below the flat plane of the main ring particles. These tiny dust motes are only a micron in size, far smaller than a grain of fine sand, and when they are lifted away from the densely packed, icy boulders that make up the bulk of the rings, they create a diffuse cloud that scatters sunlight differently. From our vantage point, this cloud appears darker than the bright rings when viewed at a high phase angle, and brighter than the rings when backlit by the sun, creating the illusion of a dark spoke or a bright one depending on the lighting conditions. The fact that they maintain a rigid, radial shape as they orbit the planet is another key part of the mystery. The inner part of the ring orbits Saturn much faster than the outer part, following Kepler's laws of motion, so any physical feature should be quickly sheared apart and stretched into a curve. The fact that the spokes remain straight, cutting directly across the gravitational flow, is a clear signal that we are not dealing with simple orbital mechanics, but with something far more subtle and complex. The leading theory to explain this bizarre phenomenon points directly to the powerful and dynamic influence of Saturn's magnetic field. The entire ring system resides within the planet's immense magnetosphere, a giant bubble of magnetic influence that rotates along with Saturn's internal magnetic field. The thinking is that these tiny dust particles, through some process, become electrically charged. On the sunlit side of the rings, this could happen when ultraviolet radiation from the sun knocks electrons loose from the dust grains, giving them a positive charge. Once charged, these microscopic particles suddenly find themselves subject to an entirely new set of forces. The planet's magnetic field, which co-rotates with Saturn, can now exert a force on the charged dust, effectively lifting it up out of the ring plane against the gentle pull of Saturn's gravity. It's a delicate balance, the electromagnetic force fighting gravity, allowing a fine mist of dust to float above the rings, creating the visible spoke. The radial shape is preserved because the magnetic field, which is locked to the planet's rotation, drags the charged particles along at a fixed rate, forcing them to move as a coherent unit despite their different orbital speeds. In this view, the spoke is a kind of magnetic ghost, a temporary structure painted onto the rings by invisible lines of force. However, the exact sequence of events that triggers a spoke's formation and dictates its brief lifespan is where the mystery truly deepens. What is the initial spark that charges the dust so dramatically and uniformly across a vast region? One compelling idea involves powerful lightning discharges in Saturn's atmosphere, or perhaps even within the ring system itself. A sudden, colossal burst of electromagnetic energy from a Saturnian thunderstorm could send a wave of charged particles out into the rings, creating the initial conditions for dust levitation across a huge area almost instantaneously. Another fascinating hypothesis looks to streams of tiny meteoroids constantly striking the ring particles. Each impact vaporizes a small amount of material, creating a temporary, localized plasma cloud of charged particles that could then go on to charge the surrounding dust. This would explain why spokes are more common during equinox, when the rings are presented edge onto the sun. At this geometry, the ring particles cast long shadows, creating steeper temperature gradients that might make the charging processes more efficient or allow electrostatic forces to overcome gravity more easily. Yet, even with these plausible mechanisms, our understanding remains incomplete. Computer models struggle to replicate the full life cycle of a spoke, its rapid appearance, its stability over several hours, and its eventual, gentle dissipation. The charged dust particles should eventually lose their charge as they interact with the surrounding plasma environment, causing them to settle back down onto the ring plane. But the precise details of this discharge process are still being investigated. The Cassini mission provided a wealth of data, but it also revealed new complexities such as variations in the spoke's seasonal appearance and their specific location within the B-ring, suggesting that the local ring environment, the size distribution of particles, and their density plays a critical role that we don't yet fully grasp. The spokes of Saturn are therefore more than just a beautiful curiosity. They are a dynamic, natural laboratory for studying plasma physics and electromagnetism on a colossal scale. They demonstrate that even a structure as seemingly simple and timeless as a ring of orbiting ice is, in reality, a vibrant and electrically active system where sunlight, magnetism, and microscopic dust conspire to create one of the solar system's most haunting and transient works of art. Now let's turn from the spectacular rings of Saturn to a world forged in fire, a planet locked in a delicate gravitational dance with the star it orbits so closely. Mercury, the solar system's innermost planet, presents a rotational rhythm so peculiar it defies simple explanation. Unlike our own moon, which is tidally locked to Earth in a one-to-one resonance, showing us only one face as it orbits, Mercury is locked in what's known as a 3-to-2 spin orbit resonance. This means the tiny planet completes 3 full rotations on its axis for every 2 revolutions it makes around the Sun. From the Sun's perspective, this creates a bizarre day. A single solar day on Mercury from one sunrise to the next lasts for 2 entire Mercurian years, or about 176 Earth days. If you were standing on its surface, you would witness a sun that appears to move erratically across the sky, at times even reversing its course in a stunning celestial loop before plunging the landscape back into darkness. This specific resonance was a monumental surprise when it was finally confirmed by radar observations in the 1960s. For centuries, astronomers had assumed that Mercury, being so close to the immense gravitational pull of the Sun, must be tidally locked, perpetually presenting one scorching hot face to the Sun and keeping one frigid side in eternal darkness. This seemed like a natural conclusion, a straightforward outcome of the relentless tidal forces exerted by our star. The discovery that it was instead spinning, and spinning in this precise 3-2 rhythm, forced a complete rewrite of our understanding of planetary rotation and tidal locking. It revealed that the process is far more nuanced than a simple on-off switch, and that a planet can find a stable, balanced state that isn't simply showing one face to its parent star. So, how did Mercury arrive at this particular, unusual rhythm? The driving force is, of course, the Sun's gravity, but the mechanism is one of subtle nudges rather than an outright break. The Sun's gravitational field exerts a tidal force on Mercury, very much like the Moon's pull on Earth's oceans. Because Mercury is not a perfect sphere, it has a slightly elongated, oblong shape. The Sun's gravity acts differently on the bulges. As the planet rotates and orbits, the Sun's pull tries to twist these bulges into alignment, creating a torque that works to slow down or speed up the planet's spin over immense timescales. In the chaotic early solar system, Mercury was likely spinning much faster. Over billions of years, this solar torque acted as a brake, gradually slowing its rotation. But instead of slowing all the way to a standstill, the planet's rotation rate became captured or trapped in the 3-2 resonance. This state is stable because it minimizes the energy lost to tidal heating. At this specific spin rate, the planet's elongated shape and its elliptical orbit work in a kind of harmony. The tidal bulges are raised most strongly when Mercury is at its closest approach to the Sun, a point called perihelion, and the resonance ensures the same hemisphere always faces the Sun at that moment of maximum gravitational stress. It's an energy-saving configuration, a cosmic compromise that allows the planet to settle into a comfortable, repeating pattern. However, the fact that Mercury settled into this specific 3-2 resonance, and not a simpler 1-1 lock, reveals critical clues about the planet's internal structure and its violent past. A key factor is Mercury's unusually large, partially molten core, which makes up a staggering 85% of its radius. This massive iron core gives the planet a relatively high density, but it also affects how it responds to gravitational forces. A molten interior can flow and deform, allowing for a different dissipation of tidal energy compared to a completely solid body. This internal squishiness likely played a role in guiding Mercury toward its current resonant state, influencing the rate at which its spin was slowed and determining which resonance proved to be the most stable in point. Furthermore, the planet's significant orbital eccentricity, its path around the Sun, is far more elliptical than that of Venus or Earth, is crucial. A perfectly circular orbit would likely have led to a standard 1-1 tidal lock. But Mercury's eccentric orbit means its distance from the Sun, and therefore the strength of the tidal torque varies dramatically. This variation breaks the symmetry and makes the 3-2 resonance a much more stable and likely outcome than the simpler synchronous rotation. Yet, even with this elegant explanation, subtle mysteries remain. The precise pathway that led Mercury to be captured in this resonance and not another is not fully mapped out. Computer models show that the process is sensitive to the planet's initial conditions. Its starting spin rate, the exact shape of its primordial orbit, and the detailed mechanical properties of its interior over billions of years. Small differences in these initial parameters could have led to a completely different present-day rotation. There's also the lingering question of whether major impacts in Mercury's early history, which carved out its vast impact basins, could have given its spin a significant kick, either pushing it toward or away from the resonance we see today. Understanding the nuances of Mercury's spin, therefore, is more than an orbital curiosity. It's a powerful diagnostic tool. By studying this locked rotation, we can indirectly probe the planet's deep interior, constraining the size and state of its core and the rheology, the flow and deformation of its mantle. This peculiar 3-2 beat is a cosmic metronome that has been ticking for eons, its rhythm encoding the secrets of the planet's formation, its internal fire, and its long, slow gravitational dance with the Sun. Leaving behind the ghostly spokes of Saturn's rings and the locked rhythm of Mercury, we venture to a tiny, unassuming world that has fundamentally reshaped our search for life in the cosmos. Saturn's moon, Enceladus, is a mere 500 kilometers across, a gleaming white marble that could easily be overlooked amidst the grandeur of the gas giant's retinue. For years, it was considered just another frozen, inert satellite. But then the Cassini spacecraft arrived, and with a single, stunning discovery, it transformed this speck of ice into one of the most promising places in our entire solar system. As Cassini swept past Enceladus, its instruments captured something that seemed impossible: colossal geysers, towering plumes of water vapor and ice crystals, erupting from deep fissures known as tiger stripes at the moon's south pole. These weren't minor puffs of frost, they were jets shooting hundreds of kilometers into space, a magnificent, ongoing cryovolcanic eruption that was actively feeding and refreshing Saturn's faint E-ring. It was a moment of pure cosmic revelation, proving that this small moon was not dead but dynamically, vibrantly alive with geological activity. The implications of these plumes were staggering. By flying directly through them, Cassini was able to perform a celestial chemical analysis, tasting their composition. The spacecraft found that the plumes were predominantly water vapor, but they also contained a surprising mix of other ingredients: volatile gases like nitrogen and carbon dioxide, and most intriguingly, tiny grains of silica and a significant amount of simple organic molecules, the carbon-based building blocks of life. The presence of salt in the ice grains was the final, crucial piece of evidence. This wasn't just water from a small, subsurface lake. The salinity and the chemistry pointed unequivocally to a vast, global ocean of liquid water, trapped between the moon's rocky core and its outer icy shell. Enceladus, a world smaller than the country of France, was hiding a sunless sea that likely held more water than all of Earth's oceans combined. This confirmation shattered our preconceptions of where life could potentially thrive. We had long focused on the Goldilocks zone, the region around a star where temperatures are just right for liquid water on the surface. Enceladus, far outside this zone in the deep freeze of the outer solar system, taught us that life's true requirement isn't a specific distance from a star, but a persistent source of liquid water and energy. It revealed that habitable environments can exist in the most unexpected places, powered not by sunlight, but by the hidden gravitational furnaces of giant planets. This brings us to the central, driving mystery of Enceladus. What is the power source? What immense force keeps a global ocean from freezing solid in the bitter cold of space, and furthermore, propels it with such violence through miles of ice and out into the void? The leading and most compelling answer is tidal heating, a process of gravitational friction orchestrated by the moon's master, Saturn. Enceladus does not orbit in a perfect circle, its path is slightly elliptical. This means its distance from Saturn changes constantly. As it moves closer, Saturn's immense gravity pulls harder, stretching the moon. As it moves farther away, the pull relaxes and the moon settles back into a more spherical shape. This constant, rhythmic flexing, this planetary kneading, generates immense friction and heat within the moon's interior. Think of repeatedly bending a metal coat hanger. After a while, the point where you're bending it becomes hot to the touch. Enceladus is that coat hanger on a planetary scale, being flexed by the most powerful hands in the solar system. But the details of this process are where the true scientific detective work begins. The tidal heating isn't uniform, it's concentrated dramatically at the South Pole. Scientists believe this is due to a feedback loop of astonishing efficiency. The underground ocean acts as a lubricant, allowing the icy shell to slide relatively freely over the rocky core. The tiger stripe fractures at the South Pole are likely the weakest points in this shell, areas where the ice is thinnest. The intense tidal friction focuses its energy there, generating enough heat to keep the water beneath it liquid. This liquid water then erupts through the cracks, releasing pressure and carrying heat away. This very eruption then allows the ice shell to shift and flex more easily, which in turn generates more tidal friction, perpetuating the cycle. It's a beautifully balanced, self-sustaining geothermal engine where the moon's own eruptions help to power the mechanism that creates them. However, the plot thickens considerably with the discovery of those tiny, nanometer-sized silica grains in the plumes. These particles are the signature of a specific and thrilling process. On Earth, silica grains of this exact size are only formed when hot, mineral-rich water interacts with rock at temperatures of at least 90 degrees Celsius, or nearly 200 degrees Fahrenheit. The only place this happens is at hydrothermal vents on the deep ocean floor, where superheated water, charged with chemicals from the mantle, spews out from cracks in the crust. The presence of these grains in the Enceladus plumes is our strongest indirect evidence that the seafloor of this alien ocean is geologically active, dotted with hydrothermal vent systems just like those found in the darkest depths of Earth's oceans. And this is where the possibility of life transforms from a tantalizing maybe into a compelling why not. On our own planet, deep-sea hydrothermal vents are bustling, vibrant oases of life, entire ecosystems that thrive in complete darkness, powered not by the sun but by chemosynthesis, the process where microbes convert the vent's chemicals, like hydrogen sulfide or methane, into energy. The recipe on Enceladus appears to be complete. A vast liquid water ocean, a rocky core leaching minerals, a persistent source of geothermal energy, and the presence of organic molecules. All the ingredients for a second genesis of life are present, mixing and reacting in the warm, dark waters beneath the ice. The geysers of Enceladus are therefore more than just a spectacular sight. They are a free sample delivery service from a hidden alien ocean, offering us a glimpse into an environment that may be, at this very moment, nurturing its own unique subsurface biology. The unresolved question is no longer just about orbital mechanics and heat transfer, but about whether we are alone, and if a tiny, icy moon a billion kilometers away holds the answer. And now we travel from the erupting water world of Enceladus to a landscape that is at once hauntingly familiar and utterly alien. The shores of Saturn's largest moon, Titan. If you could stand on its surface, you would find yourself in a world of profound paradox. The sky is a perpetual, hazy orange, the ground feels like soft, damp sand, and rolling hills lead down to the shores of vast, dark seas. You might feel a chilling breeze and even sea clouds drifting in the sky. For a moment, it could almost feel like home. But the rain that falls from those clouds isn't water, it's liquid methane. And the seas that lap against those alien shores aren't filled with water, but with a frigid, swirling mixture of methane and ethane. Titan is the only other place in our solar system, besides Earth, with stable bodies of liquid on its surface. It possesses a full, dynamic hydrological cycle, but it's a hydrocarbon cycle running at a cryogenic minus 290 degrees Fahrenheit. This is a world where the very rivers and lakes are made of the components of natural gas, creating a landscape that is a bizarre, funhouse mirror version of our own. The discovery of these lakes and seas by the Cassini-Huygens mission was a monumental achievement in planetary exploration. The Huygens probe, descending through the thick, nitrogen-rich atmosphere, gave us our first breathtaking glimpse of a drainage pattern, river channels carving through a landscape, leading to what appeared to be a dark, damp shoreline. From orbit, Cassini's radar pierced the obscuring smog to map these dark, smooth regions, confirming they were indeed immense bodies of liquid. We found everything from small, scattered ponds to vast seas. The largest Kraken mare is larger than Earth's Caspian Sea, a sprawling body of liquid hydrocarbons that could swallow many of our own Great Lakes without a trace. These are not placid pools. Cassini's data suggests they have depth, volume, and complex coastlines with bays, inlets, and even archipelagos. It is a complete, functioning geological system, but one that operates with a completely different set of physical and chemical rules. Yet within these calm, dark seas, Cassini's radar spotted something truly bizarre: features that have come to be known as the Magic Islands. On successive flybys, the spacecraft would image the same region of a sea like Ligeia Mare. In one pass, the radar would show a smooth, dark, liquid surface, but on the next pass, just days or weeks later, a bright, highly reflective patch would appear where there was once only liquid. Then, on a third pass, the bright feature would be gone, having vanished as mysteriously as it appeared. These transient bright spots were the Magic Islands phenomena that flicker in and out of existence on an alien sea. They earned their name because they seem to defy easy explanation, appearing and disappearing like illusions. So, what could these enigmatic features be? Scientists have proposed several compelling theories, each painting a picture of dynamic activity on these alien lakes. One of the leading ideas is that they are vast fields of bubbles. As the seasons change on Titan, and each season there lasts for more than 7 Earth years, the seas warm and cool. This could cause dissolved nitrogen, which is abundant in the atmosphere and can be stored in the cold liquid methane, to suddenly come out of solution, much like carbon dioxide fizzing out of a soda bottle when you open it. A massive, localized release of nitrogen gas could create a sprawling blanket of rising bubbles on the surface, which would appear brilliantly reflective to Cassini's radar, creating a temporary island. Another fascinating possibility is that they are waves. For the most part, Titan's seas appear remarkably calm, like glass. But if a wind were to pick up, even a gentle breeze, it could stir the hydrocarbon soup into a choppy surface. The rough, textured water of a wave field would scatter radar signals back to the spacecraft much more effectively than a mirror-smooth liquid, creating the same kind of bright, transient signature. The Magic Islands could therefore be the first direct evidence of weather-driven waves on another world. Other theories are even more exotic. The islands could be floating solids. On Titan, given the right temperatures, certain organic compounds can form a slushy, wax-like substance that might be lighter than the liquid methane and ethane mixture. A large sheet of this frozen hydrocarbon gunk could break free from a shoreline or form on the surface and float for a time before eventually sinking or dissolving, creating a temporary solid island. Alternatively, they could be suspended solids, a dense, suspended fog of heavy, sand-like particles stirred up from the seafloor by currents, creating a suspended plume that looks like a solid object to radar. Each of these explanations points to a world that is far from static. It is a place of constant, subtle change, where the seas themselves are alive with processes we are only beginning to decode. This leads us to the grander context: Titan's complex hydrocarbon cycle, which is a direct, albeit frigid, analog to Earth's water cycle. On Earth, water evaporates from the oceans, forms clouds, rains down, flows across the landscape in rivers, and collects in lakes and seas only to evaporate again. On Titan, methane plays the exact same role. Methane evaporates from the seas, rises into the atmosphere to form clouds, and then falls back to the surface as methane rain. This rain carves river channels and can cause flash floods. It erodes the water ice bedrock into stunning geological features, and it ultimately drains into the great seas, completing the cycle. We have seen evidence of all these stages. Cassini observed cloud systems forming and dissipating, and the Huygens probe imaged what are clearly river channels and what appears to be a pebble-strewn floodplain rounded by the flow of liquid methane. The profound, unanswered questions about this cycle are what make Titan a premier target for future exploration. The chemistry occurring in these lakes and seas is a form of prebiotic chemistry, the kind of complex molecular interactions that likely occurred on Earth before life ever emerged. The constant cycling of methane and ethane under the influence of solar ultraviolet radiation high in Titan's atmosphere is known to create a rich soup of more complex organic molecules, including the building blocks of proteins and DNA. What happens when these molecules rain down and collect in the seas? Do they interact on the seafloor? Is there a form of chemistry there that could hint at the pathways toward life, even in the absence of liquid water? The lakes of Titan are not just geological curiosities, they are immense natural laboratories for organic chemistry. Understanding the exact composition of these liquids, the nature of the sediments on their floors, and the full spectrum of the magic island phenomena is critical. It could teach us not only about the potential for life in environments radically different from our own, but also about the fundamental processes that might have set the stage for life on Earth billions of years ago. Titan's silent, dark seas, with their mysterious appearing and disappearing islands, hold secrets that go to the very heart of our quest to understand the conditions that can give rise to complexity in the cosmos. Now we venture into the most profound modern detective story in our solar system, a case built not on what we can see, but on the subtle, ghostly influence of something we cannot. Far beyond the stark boundary of the Kuiper Cliff, in the frigid, sunless expanse of the scattered disk, a handful of the most distant known objects are behaving in a way that defies simple gravitational explanation. Their elongated orbits are not randomly oriented. Instead, they are mysteriously clustered, as if an unseen shepherd is herding them, guiding their paths with an invisible hand. This is the core of the Planet 9 hypothesis, the tantalizing idea that a true giant, a world 5 to 10 times the mass of Earth, is lurking in the outer darkness, patiently completing an orbit that takes between 10 and 20,000 years. The evidence for this hidden world is entirely indirect, written in the peculiar celestial choreography of a small group of extreme trans-Neptunian objects. These are icy bodies like Sedna, whose orbits take them hundreds of astronomical units from the Sun. The curious pattern was first seriously proposed by astronomers Konstantin Batygin and Mike Brown at Caltech. They noticed that the most distant of these objects share a bizarre orbital trait. Their points of closest approach to the Sun, their perihelia, are all grouped together in the same general region of space. Even more strangely, their orbits are physically tilted in a similar way, all swooping down below the plane of the solar system and then rising back up in a coordinated fashion. Statistically, the odds of this specific clustering happening by pure chance are astronomically low, less than a fraction of a percent. It's as if you dropped a dozen marbles on a large, flat sheet, and they all spontaneously rolled to the same corner and tilted themselves at the same angle. The gravitational pull of the known planets, especially Neptune, simply cannot account for this coordinated alignment over billions of years. Something else must be holding this configuration in place, preventing these distant orbits from randomizing. According to the models, the most elegant and powerful explanation is the gravitational influence of a massive, undiscovered planet. The hypothetical Planet 9, with its immense gravity, would act as a dominant force in the outermost solar system. Its distant orbit would create a stable, resonant framework. The clustered objects we observe are essentially trapped in a gravitational dance with this giant. Their orbits are prevented from precessing or slowly rotating by Planet 9's steady pull. The physics is analogous to how Jupiter's gravity herds the asteroids in the Kirkwood gaps, but on a scale thousands of times larger. The models show that an object with the estimated mass and a highly elliptical orbit, with its perihelion pointed away from the clustered objects, can perfectly recreate the observed orbital distribution. It shepherds these distant bodies, keeping them bunched together and preventing their orbits from spreading out randomly across the sky. This hidden world would also explain other solar system oddities, such as why some objects, like the dwarf planet Sedna, have orbits that are completely detached from Neptune's influence, never coming close enough to be affected by it. Planet Nine's gravity could have sculpted these detached orbits long ago, flinging objects like Sedna into their strange, sun-secluded paths. The search for this phantom planet is one of the most ambitious astronomical endeavors of our time, a hunt conducted with the world's most powerful telescopes like Subaru in Hawaii. The challenge is monumental. Planet 9, if it exists, would be incredibly faint, reflecting only the tiniest fraction of the Sun's already feeble light from such an immense distance. Its motion across the sky would be glacially slow, making it difficult to distinguish from the background of fixed stars. Astronomers are not just looking at a single point in the sky, they are surveying vast swaths of the celestial sphere, taking multiple images of the same region over months or years, and looking for that one tiny, star-like dot that has moved ever so slightly against the static backdrop of the galaxy. It is a painstaking process, like searching for a single, slowly crawling ant on a dark beach at night. Furthermore, its predicted orbit is so vast that it could currently be almost anywhere along its 10,000-year path, forcing searchers to cover a truly daunting volume of space. Of course, such a radical hypothesis demands that we rigorously consider alternative explanations. One prominent idea suggests that the collective gravity of many smaller, unseen Kuiper belt objects could, in theory, produce a similar shepherding effect. If the outer solar system contains a much more massive disk of small, icy bodies than we currently know about, their combined gravitational pull might be enough to nudge the orbits of the extreme objects into the observed cluster. However, this alternative has its own significant hurdles. To generate the required gravitational influence, this hidden disk would need to contain several times the mass of the entire known Kuiper belt, which seems at odds with our current sensors and models of solar system formation. Another, more exotic possibility involves a primordial black hole, a remnant from the Big Bang with a mass a few times that of Earth. The gravitational effect would be identical to that of a planet, but searching for it would require detecting not light, but the telltale flashes of radiation as it annihilates nearby dark matter, or the way it might gravitationally microlens the light of background stars. Despite these alternatives, the Planet 9 hypothesis remains the most parsimonious and compelling solution. It explains multiple, unrelated orbital anomalies with a single, elegant cause. The ongoing failure to find it is not necessarily evidence against it, but a testament to the sheer difficulty of the search and the unimaginable scale of the territory we are probing. Whether it is ultimately confirmed or not, the hypothesis has already revolutionized our view of the outer solar system. It has forced us to acknowledge that our inventory of major worlds may be incomplete, and that the gravitational shadows cast by unseen giants can shape the cosmos in ways we are only just learning to perceive. The mystery of Planet 9 is a powerful reminder that the story of our solar system is still being written, and its final chapters may be waiting in the dark just beyond the edge of our current vision. After traversing the theoretical space of hidden planets and the tangible shores of alien lakes, we now confront a mystery that rains down upon us from the void, an invisible shower of atomic shrapnel whose source has long been a cosmic whodunit. This is the enigma of cosmic rays, subatomic particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light. They constantly bombard our atmosphere from every direction, a testament to the universe's raw, unbridled power. For over a century, we've known they exist, but their origins have remained frustratingly obscure. Because these particles are electrically charged, their paths are hopelessly scrambled by the magnetic fields that permeate our galaxy. They don't travel in straight lines from their source to our detectors. They spiral and curve along tangled magnetic pathways, making it nearly impossible to look back along their trajectory and point a finger at their celestial birthplace. It's like trying to trace a single raindrop in a hurricane back to the exact cloud it came from. We knew these particles were arriving, but the sky map of their origins was a featureless, isotropic blur. That is, until an observatory named Milagro saw something that shouldn't be there. Situated in the mountains of New Mexico, the Milagro Gamma Ray Observatory wasn't looking for cosmic rays directly. Instead, it watched for the faint flashes of blue light, known as Cherenkov radiation, produced when high-energy particles or gamma rays slam into our atmosphere, creating a cascade of secondary particles. By meticulously analyzing years of this data, astronomers made a staggering discovery. They found a persistent, statistically significant hotspot, a region of the sky near the constellation Taurus that was pouring out an unexpected excess of these very high-energy cosmic rays. This was unprecedented. The conventional wisdom said such a localized source shouldn't be visible. The galactic magnetic field should have smeared any point source into an indistinguishable part of the background noise. The fact that this hotspot stood out so clearly meant it had to be something special, something relatively close to our solar system, and producing particles of such immense energy that their paths were less easily bent, allowing them to point more directly back to their origin. This initial, tantalizing discovery needed confirmation, and it came from a more powerful successor, the High-Altitude Water Cherenkov Observatory, or HAWK, located in Mexico. With greater sensitivity and a wider field of view, HAWK not only confirmed the Milagro hotspot but mapped it with much finer detail. They revealed it wasn't just a vague blur, it was a defined region stretching about 40 degrees across the sky, a colossal structure in terms of celestial real estate. The existence of this feature immediately overturned a key assumption in astrophysics. It proved that, at the very highest energies, the galaxy is not a uniform fog of cosmic rays. There are specific accelerators at work, and one of the most powerful seems to be sitting right in our cosmic backyard on a galactic scale. So, what cosmic engine, what titanic natural particle accelerator is responsible for this intense, localized downpour? The prime suspect, as it often is in high-energy astrophysics, is a supernova remnant. When a massive star ends its life in a cataclysmic explosion, it creates a rapidly expanding shock wave that rips through the surrounding interstellar medium. This shock wave acts like a gigantic natural particle accelerator. Charged particles can get caught in the magnetic fields carried by the shock, bouncing back and forth across the expanding front, gaining a tremendous boost in energy with each crossing until they are eventually flung out into space, becoming the cosmic rays we detect. There is a known supernova remnant in the general vicinity of the hotspot, a structure known as the Taurus molecular cloud. It's a plausible candidate, a celestial crime scene with a potential weapon lying nearby. However, the case is far from closed. The sheer size and energy output of the hotspot pose challenges for this straightforward explanation. Is this single remnant powerful enough to account for the entire signal? Could multiple, overlapping supernova remnants from a nearby star-forming region be combining their output to create this intense concentration? The data from HAWK suggests the hotspot spectrum, the distribution of particle energies, might not perfectly match what we'd expect from a standard supernova remnant accelerator, leaving the door open for more exotic possibilities. And exotic possibilities abound. One of the most compelling alternative theories ventures into the realm of the invisible universe, dark matter. We know this mysterious substance outweighs normal matter by a factor of 5 to 1, and yet we have no idea what it's made of. One leading candidate is a hypothetical class of particles known as weakly interacting massive particles, or WIMP. If these particles exist, they could be their own antimatter counterparts. When two WIMP collide, the theory goes, they would annihilate each other in a flash of energy, producing a shower of standard model particles, including protons and antiprotons that would contribute to the cosmic ray flux. A nearby, dense clump of dark matter, perhaps the remnant of a small galaxy cannibalized by our own Milky Way eons ago, could be the site of such frequent annihilations that it creates a bright, localized source of cosmic rays appearing to us as the hotspot. The energy signature could potentially differentiate this process from a standard astrophysical accelerator, and the hunt is on for a specific pattern in the arriving particles that would be the smoking gun for dark matter. Yet the true nature of the hotspot remains elusive, and its very existence continues to challenge our fundamental models of how particles travel through the galaxy. The fact that we can see it at all suggests that the magnetic fields in our local galactic neighborhood might be much weaker or more orderly than we previously assumed, creating a kind of magnetic corridor that allows these particles to travel on straighter paths. Or it could imply that the source is so close and so recent that the particles haven't had enough time to be completely randomized by their journey. Each observation narrows the possibilities but also deepens the mystery. Is it a single monstrous object or the combined fury of several sources? Is it a sign of ordinary matter operating in an extraordinary way, or our first glimpse of the annihilation of the universe's most dominant yet hidden component? The cosmic ray hotspot is a beacon in the subatomic fog, a reminder that some of the most profound questions in physics are being answered by particles smaller than an atom, arriving from the darkness and pointing toward a hidden engine of creation and destruction just next door. Imagine a cosmic balancing act of perfect equilibrium. In any system where two massive bodies orbit each other, like the Sun and Earth, there exist 5 special points in space where the gravitational pull of the two giants and the centrifugal force of a smaller object's orbit all cancel out. These are the Lagrangian points, named after the mathematician who discovered them, and they act like gravitational parking spots. Place an object at one of these points and it will tend to stay there, locked in a stable cosmic dance with the two larger bodies. Of these 5 points, the most stable are the L4 and L5 points, which lie along the smaller planet's orbit, 60 degrees ahead of it and 60 degrees behind it. They form the points of 2 equilateral triangles with the 2 main bodies, creating zones of profound gravitational calm. And we have a stunning example of these points in action. Look at Jupiter, and you'll find its L4 and L5 points teeming with thousands of asteroids, known as the Trojan asteroids. These ancient rocks have been trapped in these stable zones for billions of years, a permanent celestial entourage for the gas giant, orbiting the Sun in perfect lockstep with their planetary shepherd. This dramatic example makes the situation with our own planet all the more puzzling. Earth also has L4 and L5 points, gravitationally stable zones in our orbit around the Sun. According to the pure mathematics of the 3-body problem, these should be natural gathering places for space debris, the dust of creation, captured asteroids, or the remnants of ancient collisions. They should be bustling way stations, cosmic crossroads where material accumulates. Yet when we look, we find them largely empty. We've sent probes and scanned these regions with powerful telescopes, and aside from a few tiny, temporary dust clouds and the occasional fleeting visitor, Earth's prime gravitational parking spots are vacant. This presents a fascinating cosmic contradiction. Why would Jupiter's stable points be filled to the brim with primitive asteroids, while our own, which obey the same fundamental laws of physics, are barren? The answer isn't that the points are unstable in theory, but that our local neighborhood in space is a much more complicated and disruptive environment than Jupiter's. The primary culprit for this emptiness is almost certainly the influence of other planets, a gravitational meddling that ruins the perfect isolation the Lagrangian points theoretically require. While the Sun and Earth form the core of the system, we are not alone. The Moon's gravity, though small, introduces constant, tiny perturbations. More significantly, the gentle but relentless gravitational tugs from our planetary neighbors, especially Venus and Mars as their orbits bring them closer to us, act like a constant stirring spoon in a cosmic cup. Over millions of years, these subtle tugs can slowly alter the orbit of any object trying to reside at our L4 or L5 points. They don't provide enough force to eject an object immediately, but they impart just enough energy to nudge it out of the delicate balance required to stay trapped. Think of it like trying to balance a marble on the top of a perfectly smooth, wide hill. In a perfectly still room, it might stay, but if people are constantly walking by, causing tiny vibrations in the floor, the marble will eventually wobble and roll away. Venus and Mars are the people constantly walking through our gravitational living room, preventing any object from settling in for the long haul. Another critical factor is the sheer timescale involved. The solar system is 4.5 billion years old. While the L4 and L5 points are stable over short periods, their stability over such astronomically long timescales is not absolute, especially in a dynamically noisy region like the inner solar system. Orbital resonances can develop. An object might be stable for 1 million years, but then its orbit might slowly precess until it enters a resonant frequency with, say, Jupiter. This resonance can act like a gravitational pump, slowly feeding energy into the object's orbit over countless cycles until it has enough velocity to escape the Lagrangian point's gentle grip. It's a process of slow, patient erosion rather than a sudden catastrophe. Any material that was originally captured in Earth's Trojan points during the chaotic early days of the solar system has likely been stripped away by this billion-year barrage of microscopic gravitational nudges. Jupiter, by contrast, is a gravitational titan. Its immense mass dominates its region of space, and its Lagrange points are far enough from the disruptive influence of the other giant planets that they have remained stable sanctuaries for eons. The objects trapped there are fossils from the solar system's birth, preserved in a gravitational time capsule that Earth's more tumultuous neighborhood simply could not provide. There's also the question of source material. For a Lagrange point to be populated, there needs to be something to populate it. The Jupiter-Trojan asteroids are likely primordial, leftover building blocks from the formation of the outer solar system that were easily swept up by Jupiter's mighty gravity. In Earth's case, any candidate material would have had to originate much closer to the Sun. The population of asteroids in the inner solar system is sparser, and the dynamical pathways for them to be gently captured into our L4 or L5 points, rather than colliding with us or being flung away, are far more limited. It's possible that our points have never been permanently occupied simply because the right objects never drifted into the right places at the right times to become trapped. Occasional temporary residents do appear, like the small asteroid 2010 TK7, which is in a complex tadpole orbit around Earth's L4 point, but it's not a permanent resident. Its orbit is chaotic and will likely be disrupted on a timescale of thousands or millions of years, not billions. These fleeting guests highlight the dynamic nature of these zones. They are stable enough for a temporary stay, but not the eternal hotels that Jupiter provides. The emptiness of Earth's Lagrangian points is therefore not a failure of the theory, but a testament to the solar system's turbulent history and complex interconnectedness. It serves as a subtle clue, a negative space that tells a story about the gravitational cleaning that has occurred over the eons. By understanding why these points are vacant, we gain a deeper appreciation for the delicate orbital choreography that governs our cosmic neighborhood. It reminds us that stability in the cosmos is often a relative term, and that what appears to be a perfectly safe harbor on paper can, in the real-world chaos of a multi-planet system, be a place where nothing can permanently settle. This quiet mystery underscores that our solar system is a dynamic, evolving entity, and the silent, empty spaces can sometimes speak volumes about the forces that have shaped our home. But just as we've grown accustomed to the enduring fury of Jupiter's great red spot, the outer solar system presents us with a storm of a completely different character, one that embodies the very essence of change. When Voyager 2 raced past Neptune in 1989, it revealed a world of astonishing, deep blue beauty, but its most striking feature was a colossal tempest in the southern hemisphere. This was Neptune's great dark spot, an Earth-sized maelstrom of deep indigo, a high-pressure anticyclone whipping around its center at supersonic speeds of up to 1,500 miles per hour. It was a spectacular discovery, a landmark feature on a distant world that seemed to echo the grand atmospheric dramas of its larger sibling, Jupiter. Yet, when astronomers later turned the sharp eye of the Hubble Space Telescope toward Neptune in the mid-1990s, expecting to see the familiar dark vortex, they were met with a profound surprise. The great dark spot was gone. It had vanished without a trace, and in an extraordinary twist, a new, similarly sized dark spot had materialized in Neptune's northern hemisphere, a doppelganger storm that hadn't been there before. This wasn't just a storm that had faded, it was a complete atmospheric reinvention, a dynamic puzzle that challenges our very understanding of how weather systems live and die on the ice giants. The transient nature of these Neptunian dark spots is the core of the mystery. While Jupiter's great red spot is a bastion of stability, persisting for centuries, Neptune's great storms appear to be fleeting performers on a constantly shifting stage, with lifespans estimated to be perhaps only a few years to a few decades. This dramatic difference forces us to look beyond simple comparisons and into the fundamental forces that drive these two gas giants. The first and most critical difference is the source of their atmospheric energy. Jupiter, as we've learned, blazes with intense internal heat left over from its formation, a furnace that wells up from below and powerfully drives its cloud bands and storms from the depths. Neptune, being much smaller, should have cooled off much more rapidly. Yet, against all expectations, Neptune also radiates more than twice the heat it receives from the Sun. This tells us it, too, has a powerful internal heat source, but the way this energy is delivered to the atmosphere may be profoundly different. Some scientists propose that on Neptune, the internal heat doesn't well up in a steady, planet-wide convection, but rather in violent, sporadic bursts. This could create a much more turbulent and unpredictable environment, where massive storms can be born from a sudden upwelling of energy, only to be torn apart when that energy source shifts or fades. Another piece of this complex puzzle is the sheer ferocity of Neptune's wind speeds, which are the fastest measured anywhere in the solar system. These hurricane-force jet streams racing around the planet create an environment of immense wind shear. A nascent storm vortex, like a great dark spot, must constantly fight against these shearing winds that try to rip its structure apart. It's a delicate balancing act. The storm must be powerful enough to maintain its own coherent rotation against this relentless tearing force. It's possible that Neptune's dark spots simply reach a point where the surrounding wind shear overwhelms their ability to hold themselves together, causing them to fragment and dissipate far more quickly than a storm on Jupiter, where the wind patterns, while powerful, are more stable and less disruptive to large vortex structures. The storm is in a perpetual battle for its own existence, a battle it seems destined to lose after a relatively short, spectacular life. The composition of Neptune's atmosphere adds yet another layer of intrigue to the behavior of these dark spots. Unlike the Great Red Spot, whose color is thought to come from chemicals dredged up from below, the great dark spots of Neptune are not simply dark clouds. They are actually holes, vast windows in the upper cloud deck of methane ice crystals. In these spots, the air is thought to be descending, clearing out the high, reflective white methane clouds and allowing us to see down into a darker, deeper layer of the atmosphere. This descending, clearing motion is the hallmark of a high-pressure anticyclone. But why do these clearing events suddenly begin and just as suddenly end? The answer may lie in the complex chemistry and condensation cycles of Neptune's atmosphere. As gases like methane rise and fall through layers of different temperature and pressure, they condense into clouds and then evaporate again. A small change in stability or a burst of internal heat could trigger a massive sinking of air, punching a hole in the cloud deck and creating a dark spot. Then, as atmospheric conditions shift, that sinking motion could stop, allowing the high-level methane haze to quickly reform and erase the dark spot from view, almost like a celestial eraser wiping a feature off the slate. The ultimate enigma is the appearance of a new spot in a different hemisphere. This suggests that the processes that birth these giants are not random, but are tied to the deep, global circulation patterns of the planet. It's as if Neptune has specific storm nurseries that become active in cycles. The internal dynamics of the planet, the slow churning of its fluid interior over thousands of kilometers, may periodically focus energy in certain latitudes, triggering the formation of a new great vortex. The fact that we have now observed several of these dark spots come and go, each with a limited lifespan, tells us that we are not seeing a single, unique event, but a recurring and fundamental aspect of Neptune's climatology. The planet seems to have a rhythmic, if unpredictable, pulse of storm creation and destruction. Unraveling this rhythm is crucial because it offers a stark contrast to the other giant planets. Studying why Neptune's storms are so ephemeral helps us understand the full spectrum of planetary atmospheric behavior, revealing how factors like internal heat flow, wind shear, and chemical composition combine to create worlds of enduring calm or constant, beautiful turmoil. The changing face of Neptune reminds us that stability in the cosmos is a rare and special state, and that some worlds are forever dancing to a faster, more chaotic beat. From the swirling, transient storms of Neptune, we journey inward to the stark, rust-colored plains of Mars, where the very ground beneath our rover's wheels holds its own intricate puzzles. Among the countless impact craters that scar the Martian surface, a rare few stand out not for their size but for their bizarre and beautiful shape. These are the so-called dragonfly craters, geological formations so peculiar they seem almost like works of abstract art carved into the landscape. Imagine a typical bowl-shaped crater, but then picture a second, distinct inner ring, not concentric like a bullseye but offset, creating a structure that looks remarkably like the delicate, segmented body of a dragonfly when viewed from above. This bilobed or double ring morphology is a dramatic departure from the norm, and its existence points to a far more complex geological story than a simple asteroid slam. The key to understanding these strange craters lies in recognizing that Mars is not a uniform ball of rock. It's a world with a complex subsurface history, layered with different materials that behave in very different ways when subjected to the cataclysmic force of an impact. One of the most compelling hypotheses for the dragonfly craters involves a precise and violent sequence of events, beginning with a very specific kind of impact. Instead of an object striking the surface head-on, the theory suggests an oblique impact where the asteroid or comet came in at a very shallow angle, perhaps just 10 or 15 degrees above the horizon. This glancing blow would have scoured a long, elliptical trench across the surface, but the real magic happened moments later, deep below the ground. Mars is known to harbor vast reservoirs of water ice just beneath its surface, a layer known as the cryosphere. The leading idea is that this oblique impactor plowed directly into a region where this subsurface ice layer was particularly thick and close to the surface. The immense energy of the impact would have instantaneously vaporized a colossal volume of that buried ice. This sudden conversion of solid ice into a massive bubble of superheated steam would have acted like a secondary explosion, a subterranean bomb going off right after the initial strike. This underground blast would have violently pushed upwards on the overlying rock, causing the ground to bulge and then collapse in a very specific pattern. The result isn't a single collapse crater, but a dual collapse, the initial elongated trench from the oblique impact, and then a second rounded depression caused by the steam explosion, creating that distinctive dragonfly body shape. The two rings, therefore, represent two separate but intimately linked cataclysms, the kinetic energy of the impact and the thermal explosion of volatiles fused into a single, lasting scar. But ice isn't the only suspect in this geological mystery. Another school of thought points to the deep-seated tectonic forces that have shaped Mars for eons. The region where some of these craters are found, Nili Fossae, is a network of deep fractures and grabens, essentially a giant crack in the Martian crust. This area is geologically stressed, pulled and stretched by forces from within the planet. The hypothesis here is that the impact itself, regardless of its angle, may have simply been the trigger that released built-up tectonic strain. When the asteroid struck, the shock waves could have traveled through the pre-stressed crust, causing the ground to fail not in a simple circular pattern, but along these hidden lines of weakness. The resulting crater wouldn't form symmetrically. Instead, it would preferentially collapse along these tectonic faults, creating the offset, bilobed structure we see. In this scenario, the dragonfly shape is a fossilized snapshot of the hidden stress field that existed at that exact location billions of years ago, with the impact merely acting as the chisel that revealed the underlying template. What makes these craters so fascinating for planetary scientists is that they are not just curiosities, they are direct probes into Mars's hidden layers. By studying their precise shape, size, and distribution, we can infer the past distribution of subsurface ice, map out ancient tectonic patterns, and understand how the Martian crust responds to extreme stress. Each dragonfly crater is like a natural drill core, exposing processes that normally occur deep underground. The ongoing debate between the ice explosion model and the tectonic control model highlights just how dynamic Mars's history has been. It's likely that both processes have played a role, perhaps even interacting in ways we haven't yet modeled. A shallow impact into an icy, tectonically stressed region could produce a uniquely complex morphology that blends both mechanisms, a signature that we are only now learning to read. These enigmatic formations remind us that every scar on a planet's surface tells a story, and sometimes the most compelling tales are told by the scars that break the mold, offering a cryptic but valuable window into a world's wet and active past. And now we arrive at a mystery that strikes at the very heart of our solar system, a paradox that doesn't involve a distant object or a fleeting signal, but our own sun. It's a profound disconnect between what we see on its surface and what we hear from its depths, a conflict known as the solar abundance problem. Imagine trying to understand a person by both their appearance and their heartbeat. Now imagine those two sources of information tell you completely different, contradictory stories about that person's fundamental nature. That is precisely the situation we face with our nearest star, and it has thrown our most trusted models of stellar physics into a state of quiet crisis. The story begins with a seemingly straightforward task, figuring out what the sun is made of. For over a century, our primary tool for this has been spectroscopy. By carefully dissecting the sunlight that reaches us, splitting it into its constituent colors like a prism, we can identify the unique chemical fingerprints, the dark absorption lines, imprinted on it by elements in the sun's outer layer, the photosphere. It's a powerful and proven technique, and for a long time we thought we had a reliable census of the solar composition, particularly the amounts of key elements like carbon, nitrogen, oxygen, neon, and iron relative to hydrogen. This established set of measurements became the foundation, the assumed chemical recipe we would use not just for the sun, but as a template for other stars. But then came a new and powerful way of listening to the sun, heliosismology. This remarkable science studies the sun's global oscillations, the constant, rhythmic pulsations that ripple across its surface like waves on a vast ocean. By meticulously tracking the frequencies and patterns of these oscillations, scientists can essentially perform a celestial ultrasound, probing deep into the solar interior. The way these sound waves travel and resonate is exquisitely sensitive to the Sun's internal conditions, its temperature, density, and crucially, its chemical composition. When researchers constructed sophisticated computer models of the Sun's structure based on the spectroscopic recipe, and then compared the predicted oscillation frequencies from these models to the actual frequencies measured by heliosismology, they expected a near-perfect match. Instead, they found a stark and troubling mismatch. The models were wrong. The Sun's internal vibrations were telling a story that the light from its surface was contradicting. The core of the discrepancy lies in what's called the convective zone boundary, the depth at which the Sun's churning, boiling interior gives way to a more stable, radiative region. Heliosismology provides a very precise measurement of this boundary depth. However, the standard solar model, built using the spectroscopic abundances, predicts a boundary that is significantly shallower than what the oscillations reveal. It's as if the heartbeat suggests a much larger heart than the outward appearance would indicate. This mismatch points directly to a problem with opacity, which is a measure of how easily radiation can travel through the solar plasma. The calculated opacity in our models is too low. The interior is more transparent than it should be, allowing energy to flow out too easily and altering the modeled structure. The most likely culprit is the initial chemical recipe. To make the models agree with the heliosismic data, we need to increase the abundance of heavier elements, which are more effective at blocking radiation. A higher opacity would trap energy more effectively, leading to a deeper convective zone that perfectly matches the observed oscillations. This presents a profound dilemma. Do we trust the centuries-old technique of spectroscopy or the modern revelations of heliosismology? The implications of this choice are staggering. If the spectroscopic measurements are correct, then our fundamental understanding of how radiation interacts with matter in the extreme conditions inside a star is flawed. Our entire set of opacity calculations, which are foundational to astrophysics, would need a major revision. This would not just affect solar models, it would send ripples through our models of every star in the universe, forcing us to reconsider their life cycles, ages, and behaviors. On the other hand, if the heliosismology is correct and the spectroscopic abundances are wrong, then we must confront an equally challenging puzzle. Why would our measurements of the Sun's surface composition be so far off? Some scientists have proposed that the photosphere we observe might not be perfectly representative of the bulk Sun. Perhaps there are subtle, yet unaccounted for, processes in the Sun's outermost layers that slightly alter the apparent strengths of the spectral lines, fooling our measurements. There's even the more exotic possibility that some mysterious process has settled heavier elements slightly deeper into the Sun, leaving the photosphere artificially depleted. The solar abundance problem is a humbling reminder that the most fundamental objects in the cosmos can still guard their deepest secrets. It forces us to question the very tools we use to understand the universe, revealing that a discrepancy of a few percentage points in the amount of oxygen or neon can unravel our most sophisticated simulations. This isn't just an academic debate, it's a quest for a more complete theory of stellar matter. Resolving it will require either a revolutionary improvement in our laboratory measurements of atomic physics or a dramatic rethinking of the complex dynamics churning within our star. The Sun, the giver of light and life, still holds a fundamental mystery in its core, a silent vibrational code that we have yet to fully crack, reminding us that even our closest star has not yet yielded all of its truths. And so our journey through 25 of the solar system's most profound enigmas comes to a close, from the haunting magnetic memory of our own moon to the hypothetical giant world that may be shepherding the frozen fringes of our cosmic neighborhood. We have wandered through hexagonal storms and vanishing dark spots, contemplated geysers on a tiny, icy moon and silent lakes of methane on a smog-shrouded giant. We have listened for a whisper from the stars that never repeated and chased phantom forces that turned out to be the gentle push of escaping heat. This incredible tapestry of mysteries reveals a solar system that is not a static, well-mapped museum, but a vibrant, dynamic, and deeply strange frontier. It's a place where worlds roll on their sides, where rings paint transient patterns with charged dust, and where the very composition of our sun remains a subject of intense debate. Each anomaly, whether a fleeting radio signal or a billion-year-old orbital resonance, is a testament to the fact that our understanding is wonderfully incomplete, a mere first draft in an epic story of cosmic discovery. These puzzles are far from being mere intellectual curiosities. They are the very engines of exploration. The baffling behavior of Martian methane is precisely why we send rovers like Perseverance to sniff the air and analyze isotopes. The confirmed global ocean on Enceladus, with its tantalizing hints of hydrothermal activity, has catapulted that tiny moon to the top of the list for future missions designed to fly through its plumes and perhaps even one day land on its icy crust. The strange clustering of distant objects drives the relentless, painstaking search for Planet 9, pushing our telescopes and our data analysis techniques to their absolute limits. Every mystery we have explored today represents a direct challenge to our models and our assumptions, forcing us to build better instruments, design more ambitious spacecraft, and refine our theories of physics itself. This cycle of question and answer, of mystery and mission, is the lifeblood of science. It transforms our wonder into a focused, determined effort to peel back the layers of the cosmos, revealing not just answers but inevitably new and even more profound questions we could not have previously conceived. As we stand on this threshold of discovery, looking out at a solar system brimming with secrets, the conversation does not have to end here. The true power of this cosmic curiosity lies within a community of explorers, and that includes you. We have traversed these 25 phenomena together, but which one captured your imagination most powerfully? Does the silent, geometric perfection of Saturn's hexagon haunt your thoughts? Or does the explosive potential of a hidden ocean on Enceladus fill you with a sense of awe? Perhaps the notion of a vast, unseen planet lurking in the darkness sparks your own theories about its origin and nature. I want to hear from you. Share your favorite mystery in the comments below and tell me why it resonates with you. What are your own hypotheses for the Tunguska event or the true nature of Tabby's star? This is how we build a community of cosmic wonder, by sharing our fascination and collectively pondering the universe's greatest puzzles. If diving into the unknown like this fuels your curiosity, then consider subscribing to the channel. We are committed to bringing you more deep dives into the universe's most captivating enigmas, from the depths of black holes to the search for life beyond Earth. The cosmos is vast, mysterious, and waiting to be explored, one question at a time.